Hello guys, welcome back to TechDose, and in this video we will look at the matrix exponentiation from scratch. This particular session is from the live classes of number theory. If you are looking to prepare for difficult online assessment, like sometimes it comes in Amazon, or you want to particularly prepare for the difficult DSA rounds of Google or some kind of high frequency trading companies like the Towers Research Capital or other such companies like Code Nation, or you want to, let's say, level up in your competitive programming journey, then you can consider this number theory live course. This particular video is focused only on the matrix exponentiation, but we will touch a lot of topics which will definitely be very helpful in upskilling yourself. So you can contact us on this WhatsApp number to register, or you can visit techdose.co.in, and under the courses section you will find it. It will definitely be a very good investment in yourself. Now let's get started with the session. The prerequisite of matrix exponentiation is binary exponentiation, and we have already done that in some past class. So you know all about binary exponentiation. So let me just open the matrix part. We'll do it. Any question before we start? Also, prerequisite is you know about matrix multiplication, right? I hope you know how to multiply matrices. So I'll give you a quick overview and then we will get started. Assignment I have already updated for matrix exponentiation. 4 problems I have added. Within that, one is your homework, the 4th one. And I have also added my video link for that. So if you cannot do with matrix exponentiation, then you can look at the answer. I have already made a video using matrix exponentiation on that. So let's get started. What is matrix exponentiation and how it is different from any other technique? So you know the exponentiation techniques, exponentiation. And exponentiation means that you calculate a to the power of n, simply a to the power of n. In this, how you calculate a to the power n, what is the dimension of a matters. So if a is just a single number, integer number, then you can solve it using binary exponentiation. Direct binary exponentiation you do, and you will solve it in log n time, right? You can solve it in this time. But if A would have been a matrix, like it can be a rectangular matrix of the order P by Q, if it is of the order of P by Q, then we will not be able to do it directly by binary exponentiation because it is not in the standard format of a number. And in such case, we will do exponentiation, but instead of calling it directly as binary exponentiation, we will call it matrix exponentiation, which will be internally relying on the binary exponentiation. Okay. So first I'll tell you about what is matrix exponentiation, what type of problem fall into this category. How do you know that the problem comes and I can do matrix exponentiation? Because that's the most important question. Learning the technique is not the most important one. That is the second most important. The first important thing is how do you recognize if a problem is solvable by this technique, right? So let's get started. Now, there are two things that we should know. First, I will be talking about the technique, and once we are through the technique, then I'll tell you about what is the general pattern of problem that falls into this category, what type of problem you will find in the interview which falls into this category, and later then we will do some live coding and try to practice. Okay, so these are the three part in this live class. So let's get started. Okay. Uh, Now you know about, do you know about matrix multiplication? If I have to multiply A with B and get a result C, then you know that if this is P by Q, this has to be Q by R so that you get the dimension as P by R. So that the column here and the row here should be the same. Otherwise, multiplication wouldn't be possible, right? That is always true. Okay. And this is the resultant matrix of the multiplication, which is C having the row of A and the column of B. If you have chain multiplication A by B by C, which has dimension P by Q, Q by R, R by S, then you will get a resultant matrix D of the first matrix row and the last matrix column dimension, right? So this is how you multiply. If you have to multiply matrix, let's say it is having value A, B, C, and let's say A, B, C, D, E, F with something like P, Q, R, S, T, U, V, W, X. Can we multiply this? Can we multiply this?
No.
This is of dimension 2 by 3. This is of dimension 3 by 3. So yes, we can multiply, right? So the column here and row here is same. And what would be the resultant matrix? It will be of 2 by 3 size, which is the row here and column here, right? If you are thinking about what will be the first value, it will be equals to, you multiply this row with this column and keep adding the values. Like you have to write A times P plus B times S plus C times V. And that will go to this first value. Let's call it A1, and this will be equals to A1, right? And you fill it up with the rest of the values. Like again, with for the same row, you go second column, third column, and that is how you fill the three values. And then you repeat the same with the second row and going one column after another and filling all these three values, right? So that's how you do matrix multiplication. Now I need you to write the code, right? Like right now you have to write for multiplying two matrices which are square matrices. Two square matrices, or let's say if I give you a matrix A of dimension P by Q, and you have to multiply B by B with the dimension of Q by R. You can take it as a homework as well, but since we are going to do the live coding, you have to write the code for it as well. Okay. So can you write it right now? I will simplify this question and say that all the dimensions are same. I am taking a square matrix, multiply one square matrix with another square matrix. Can you do that? Like P, Q, R are all same values. P equals Q equals R. So you can either write a generalized code based on P, Q, R, or you assume that it is equals to D, which is dimension, and write it accordingly. Can you write this logic into code format right now in your notebook? I'll wait for 1 or 2 minutes. Please write it and then I will write it. You can verify your answer. You know this logic, right? Please write it ASAP. If you have a laptop, then it would be better that you type it in the laptop, and when we do the coding, you can copy paste it. Or maybe retype it again, whatever is the case. If you prefer making note, then please make note. I want you to implement this logic. Multiply one matrix with another matrix where multiplication is guaranteed to be possible. You don't have to check if the column is equals to row. If the question, if you think that I have to check, you can always check it later on, right? But here I'm guaranteeing that it is present. You can multiply. So let's multiply. So when I write the code, I will be assuming that I will take a square matrix having the dimension D. Because matrix exponentiation is all about finding the square matrix. Uh, anyway, we will see about that later. But you can write it in any way with PQR or with just D. All the values PQR are same. Whatever way you prefer, you write. So let me start writing as well. Uh, yeah, let me start writing. So I can keep the function type void. If you want to return, you return it. Multiply matrix. So in interview, naming is very important, and you write the camel case for function name and underscore naming for the variable names, underscore separated words. You follow different convention for variables and function naming. I hope you do that already. So here I will be taking A with certain dimension P, Q, but I will assume that all the dimensions are equals to D. Okay, and B with the dimension Q, R. So you can ignore these dimensions and say that I will be taking dimension D. Okay. Now I need to store the result of multiplication and store it in a separate matrix. If I have to store it in a separate matrix, I know that P equals Q equals R equals to D. Okay, it is a square matrix. Then I will be storing it into a resultant matrix of size D plus 1 by D plus 1. Okay, and I can predefine this matrix with the value 0, isn't it? Or you can define all the values later on as well, whatever way you prefer. If you define it with vector, then it will be initialized with a 0 value by default. So you check whatever you initialize it with, and then you can write for loop. So first one we will write for the rows. If we have to multiply two matrix, then you know that I have to go row wise. One row, second row, third row, one column, second column, third column. So for each row here, I have to go for all the columns, right? So how many rows I have to go? D rows, right? And so I'm not giving bracket. I'm just using indentation. And then for each row, I have to go for so many columns. So how many columns I have to go? Till D. Okay. So now I am traversing each row. So I am going to ith row. And now J will tell me about which column I am seeing. So if I have to calculate the result here, if it is of D by D size and this is of D by D size, then this is also of D by D size. Now you think about the first value. This first value will be a summation of all the corresponding multiplication and added values, right? To multiply and add, right? So this value, this matrix, I have named it as result. So if this matrix name is result, then which coordinate I am filling? It will be defined by the I coordinate here. Will it not be defined by I coordinate? Isn't it? Because
Yeah.
for this row, I will be filling this row here. Is it? I think so. You might be getting confused, like how are we filling the values? But for this row and this column, I'll fill the first value. The second column, I'll fill this value. Third column, I'll fill this value. So for the ith row, I am filling the ith row of the result. So I result at I should correspond to the correct row that I'm trying to fill. So what should I write? Since I have not initialized the result with zero value, since I have not initialized the result here with zero value, I will be writing result at ij equals to 0 because I will be adding, and in this simple notation, it can take some garbage value. So just to avoid that, I will be making it 0 initially. And then I have to take another iterator, isn't it? I have to take another iterator. So what should be the third iteration? Let's say it is k equals 0 to k less than dimension
E.
plus plus. Okay.
Mm.
Now, what should be result at ij?
Result ij plus equal to A of ik plus B of kj
Result ij
plus
plus
equal to
equals a at
A of
I
ik and
ij.
ik
Okay.
plus
Ik
plus B of kj
b of.
kj.
Okay. Have you all got the same thing?
So, should I have kept a like an variable instead of this third for loop?
Your voice is very low. If you can repeat it.
Is it better now?
Yeah.
Yeah. No, so I've kept a variable, like a column variable, which I will increment after the second for loop.
Okay.
It's like I
Yeah,
didn't use the third for loop.
yeah, it is fine. Like, it is
Yeah.
not the only code that you can write. So if you have written in any way, it's good. It's not a problem. Okay, but the idea should be like my result should be updated with the same time complexity. Okay, with the same time complexity, my result should get updated. So will it update the result? It should update the result. You can check it. It will update the result. Okay, it will update the result and it will keep the result in result. Now I have kept a void function. So if you wanted that A should be retaining the result of multiplication, then you should take it with ampersand. That means pass by reference. And you have to copy the result to A. Copy the values. I mean, you cannot just write A equals to result in most of the cases. You have to go item by item and copy the values, right? So we will see that I will be passing by reference and I will be copying the values to the of the calculated result to my A value. If you have to do like this, another way to do is you take the return type as the matrix and you return it. Okay, so in any way you can solve and this is the matrix multiplication in order of d cube, right? There are three loops of size d, each of them, and d cube is the complexity of this. Okay, now you know about matrix multiplication. So we should go ahead to the next part. I don't know why this hand is getting raised all the time. So uh, the next part is about, do you know identity matrix? Identity matrix, when it is used, whenever you have to calculate certain result, it has to start with 1. If it is a multiplier type result, then the starting value should be 1. If it is a plus type result that you are trying to do, then you should start with 0. So this one value is actually in matrix format. It is called identity matrix in a way that if you take matrix M and multiply with the identity matrix, you should get M of the same dimension, right? So let's say that M is of 2 by 3 size. Then what should be the dimension of identity matrix?
3 by 3.
3 by 3, right? It should be 3 by 3. And you should get again 2 by 3 because you know the result is 2 by 3 and this is 2 by 3. So here you take the column here and you take the row of this one. I mean, not the row of that one. It should be 3 by 3 only. So how do you construct an identity matrix of 3 by 3 size? 1, 1, 1, and you write 1 in the diagonals and you write 0. So this is a 3 by 3 identity matrix. So only the top left diagonal that you have should be having value 1. Other than that, you can have 0 values, right? So in order to construct an identity matrix, you can create a matrix of size 3 by 3 or whatever is the dimension square matrix, and you just assign the diagonal with one value using one for loop. You can do that. Okay, so you can write for I equals 0 to I less than D, I plus plus, and you write identity matrix at I equals 1 and preset all the values to 0. So that's how you create the identity matrix. Okay. Now, what is the meaning of me telling you all these things? If you review the code of binary exponentiation, what we are trying to do here is we are trying to find a to the power of n. The problem of matrix exponentiation is the same as binary exponentiation, just that we are trying to do it on matrix, not doing it just on an integer value. You are already knowing the solution or what to do to find 2 to the power 7 using binary exponentiation, how to do it. 2 to the power 8 using binary exponentiation, how to find it. So in this particular case, I'm telling you that if you have 2, 3, 1, 2, I have to find 2, 3, 1, 2's eighth power, then what should be the matrix answer here? Okay, so I'm trying to do the exact same thing, but I'm doing it for a matrix instead of doing it for integer. And later on, after understanding how to do it, we will see how it is applicable on problems. Okay. So I think let's try to understand how to do it. So our main goal is to find a to the power of n. Do you know? I think you remember binary exponentiation where I said that square the base and half the exponent all the time.
Yeah.
Okay. And if you keep on doing, then you will do it in order of log of exponent time. Right. That is my goal. So I have to always find the square of the matrix. How do you calculate the square of the matrix? If you have this matrix, can you calculate the square? Square means multiply with the same matrix and you get the square. So if you know how to do matrix multiplication, that's why I said that P, Q, R are all same, because the same matrix are getting multiplied. So if you multiply the same with the same matrix, then, and if the matrix is already a square matrix, then the answer will be a square matrix multiplied by square matrix. I think you know now matrix multiplication how to do. Even if it is rectangular, you can do it. But I'm telling you that now you know how to find from m. You can calculate m square using this piece of code. Okay. Now let's understand what happens if you had m to the power of 3. Because in the past case, what I did was, if you had 2 to the power of 3, then you will convert it to 2 to the power 2 times 2 to the power 1 and store it in a result which was starting with a 1 value. And multiply this power 1 and store all the power 1s in the result. And you will square the base and half the exponent. So this will be converted to 4 to the power of 1. And how will you divide it? You will divide it in 4 to the power 0 and 4 to the power 1. And this will also get multiplied in the result. And finally, you will end up with the power 1. Definitely, it will be accompanied with the result. And the result will get the final answer. Isn't it? That is the idea of binary exponentiation. If you want to recall and write the code of binary exponentiation, then maybe I have already shown you the code, but let me repeat it again. Integer base, and let's say I write base and exponent. Always write in the long format, int 64, or the long format. Don't write in integer format most of the time in exponentiation problems. So what you have to do, you have to define a result equals to 1, and then you have to do until your exponent becomes 0, or you can write exponent greater than 0. And what you have to do, if exponent is odd, then you have to store in the result 1 power of the base. So just multiply base with the result, and then exponent can be subtracted by 1 value. So 1 power is gone, accommodated in the result. And after this, it is not an else part. It is just outside of the if. It will definitely run. Square the base. How will you square the base? Base equals base into base and half the exponent. So you can right shift it by 1 time or just divide it by 2. Okay. So that should give you the final answer. What do you think? This is your binary exponentiation. Return the result. So result is containing the answer. Base is not containing the answer. Result is containing the answer, right? So why I have given you this? Because matrix exponentiation is the exact same as this one. On top of this, you should have a utility function, which is matrix multiplication. Now in matrix exponentiation, you need two functions, which is binary exponentiation and matrix multiplication. So this is an extra part, because in order to calculate square in binary exponentiation, you just multiply this. But if base was actually a matrix, then can you just write m times m? You cannot do that. So you have to call this function matrix multiply and pass the same m's here and get the result back. Understood? That is why this is an extra overhead in the utility function. So if I can calculate, let's say, a to the power n in order of log n time, in case of binary exponentiation when a was an integer, then if a was not an integer but a matrix of size d by d, then don't you think calculating a to the power n will take d cube times log n? For the matrix exponentiation, it should take d cube times log n because d cube is done in every matrix multiply code. This code. What do you think? Right? Because this step is taking order of one here. This one is taking order of one in case of binary exponentiation. But in case of base being a matrix, it will not be order of one. It will be d cube time complexity where d is the row and column. Yes. Yes, Amar.
Yeah, so Surya, over here where you say while exponent, what does this mean?
While exponent means while exponent do not become zero. So I'm
Okay,
assuming that you have given a positive value. If you want to be more exact, then you can write exponent greater than zero simply,
got it. Okay.
so that you can avoid the chance of negative numbers, right? So I think finding out the a to the power n is clear for the matrix. Anyway, we are going to write the code, okay, at the end. So we should not be thinking so much. You should just think that is the idea clear here. How I am correlating this with just the binary exponentiation and why we have to write matrix multiply. Is this clear? Right? Because the normal integer, you don't need, it is a trivial operation. But in case of matrix multiplication, it is non-trivial, taking order of d cube time. Okay. So finding a to the power n in matrix exponentiation is order of d cube log n. In binary exponentiation, it is order of log n. Matrix exponentiation, binary exponentiation is the same thing. But in matrix exponentiation, it is binary exponentiation plus matrix multiplication. Okay. So binary exponentiation is done in combination with matrix multiply. That's all. So if we are multiplying the matrices, then how will you change this code? Can you let me know what will be the changes in what is base here? Base is actually, let's say, m, and exponent is m to the power of n. So let me write it in small letter so that I know it is not the matrix. I will write the matrix in the capital letter. So m to the power n is what I want to calculate. Then what will be the result here? I should also know the dimension of m, right? So either I already know the dimension or I pass the dimension as d, integer d. Then my result cannot be defined like this. Instead, I should define the result as integer result d by d, something like this. And initialize with some value or don't initialize it. It is up to you what you want to do. Okay. If you don't initialize, it will take garbage value and you have to initialize somewhere zeros. Uh, Better to use a vector or something and then initialize with a zero value, or do a memset function here and apply the zero, you know, definition to this. So whatever way you do, you have to take this thing. Okay. Now, result is d by d, but what exactly is result? Result is storing the one powers, isn't it? And it started with one. So that means what should be the value here? It should be an identity matrix of dimension d by d. And how should you define an identity matrix of dimension d by d? This is the exact same code. How you define it? We will bring all of this together in a problem while coding. But I think you do understand, right? How we define an identity matrix. After defining an identity matrix, this exponent will be changed with the n value that I want to calculate m to the power of n. So let it be exponent only. Let's not do a lot. I am trying to find m to the power of exponent. Okay. If the exponent is odd, then what should I do? I should do result into base. So can I do result into base? I cannot do this. I have to call matrix multiply and pass result and base, and it get the result changed, updated to the new result, isn't it? Result should change, base should not change. So I can pass by reference only the first uh, parameter, which is the result. Or you can also have a return value, but I don't like return values a lot. So pass by reference is clean. So I can take pass by reference for the first and I can just multiply in the matrix multiply code, and I will not do anything. I will just change this first. I have taken this by reference, others are not taken by reference, and it will take care of everything.
I have a small question here.
Yeah.
Why the result in the previous example it has like a size of t plus 1 and d plus 1, whereas in this one it's of size t and d?
I
In
mean,
this one,
which example you are saying?
the previous one, just if you can go
Which
one step
example?
back. Yeah, in this result, it has a size of d plus 1 and d plus 1. That's the
Oh,
dimension.
so
Whereas,
okay. I mean, you can give d by d.
okay,
Yeah.
yeah.
I mean, I'm used to defining more size, but yeah, you can give d by d. It's correct. Okay. So anyway, I think till this point we are clear. This exponent definition is correct. This odd checking is correct. Matrix multiply you have to call here. Matrix multiply you have to call at this point. Saying base and base. You have to pass base and base. And everything else remains the same, but you cannot return the result. I mean, if you want to return, then you return. Otherwise, you can keep a void type and you can pass this as reference, and you know that whoever is the caller will get the result automatically. So it is up to you how you do it. This is the idea of exponentiation. Now let us look the use cases, right? Because you know how to do it, all these things. Let's look at the use case. Before looking at the use case, I would like to give you a practice example. This I have not added in the assignment. It is up to you whether you solve it. MPOW from Sphere Online Judge. You can go and solve this. It is based on, it is called power of matrix. Okay, so this is directly matrix exponentiation, but I think lead code also has these problems. So why should we go to any other thing, right? So I've added 4 lead code problems in the assignment. So those are good enough. Okay. Hmm. Can you tell me what will be the identity matrix of this matrix? Let me define this matrix. 3, 2, 1, 2, 3, 4. If this is the given matrix, what will be the identity matrix of this matrix?
Three cross three.
3 by
3 by 3,
3. Give it
3
to
by
one
3,
more. Yeah, 3 by 3.
1, and 0, 0.
I mean, yeah. Okay, 3 by 3 matrix. So this is the identity matrix. Okay. So remember this, how to compute identity matrix. Now, matrix exponentiation use case, the most important part. Matrix exponentiation, never use it anywhere else except for where I'm saying uh, it is applicable for linear recurrence relation. Linear recurrence relations. I'll tell you what all things are linear recurrence relation, how to solve it. We have seen one part only. We have seen how to do exponentiation, but there are other parts to this problem solving that we will now try to look at. The main part will start now. So matrix exponentiation is applicable only for linear recurrence relation. Sometimes it can be applicable on some other recurrence relations too, but we will not know if it is working correctly. We have to do mathematical proofs. And there is no such proof which shows that it will work on non-linear recurrence relation. So always use it on linear recurrence relation. Now let's try to understand what is a linear recurrence relation. Uh, you know Fibonacci series? That is a linear recurrence relation. So what is the function of Fibonacci? F of n equals f of n minus 1 plus f of n minus 2, right? This is a linear recurrence relation, degree 1, simply. You can have some constant multipliers, you can have some additions, but it will not affect anything. It is a linear recurrence relation. Okay, it should have some base values as well. Definitely, whenever you have the problem, you will always get some base values, or you can always derive the base value. So what is f of 0? It is 0. F of 1 is 1. Okay. let's say that the question will never say about any kind of linear recurrence relation many a times. If the question is easy, then it will be given. If the question is not easy, then it will not be given. So Fibonacci is an easy question. So there you will find this linear recurrence relation is already given. So we will try to solve one easy and one hard problem so that you can transition and understand like how you can actually derive these recurrence relations from seeing a problem. Okay. So first let's understand that, okay, the recurrence relation is given. What to do with that? Right. So let's try to first understand how to take a recurrence relation and solve it with matrix exponentiation. Then we will go again one level up and try to derive the recurrence relation from some other problems. Okay. So let's say you know how to derive recurrence relation or it is given in the code. It is given right here. Okay. So this will say that if I want to move to the next state, then what previous state answer should I know? Okay. What previous state answer should I know? So I know the base cases f of 0, f of 1. You can also derive many more answers, f of 2, f of 3. But if I ask you the 1 millionth Fibonacci number, then it will be difficult for you to just keep on finding one by one, isn't it? So definitely there is a way to do it by DP approach simply, or just by adding without DP, just use the previous two values and keep on going in order of n solution, right? Isn't it? If you have to find nth Fibonacci number, then you will iterate and keep on finding the previous two. Starting with the two values, you can find third, and then you can find fourth, fifth, and so on. So you know the standard solution order of n. Okay. I want to do some different solution and maybe optimize if possible. Now in this case, what I'll try to do is in matrix exponentiation. So I'm giving you the pattern of matrix exponentiation. You will have a certain state called nth state. I will say Sn. Okay. To this, you multiply a magic matrix M, and you go to Sn plus 1th state. Or generally in notebooks, I think in books, it will be mentioned that you start from n minus 1th step, you take a magic matrix and you will reach to nth step. Okay. Now, this M should be raised to certain power in such a way that it will allow you to directly go from the first step to some answer step, nth step, if you can calculate the m to the power of exponent. Okay, it may not be very, logical. So let me just tell you that from n minus 1th step, you multiply with the matrix and you go to the nth step. Is this point clear? Okay. Now, if you haven't yet understood, like how to do that, and what is this Sn minus 1 and what is this Sn, then let me tell you about this is called state vector. So if you have done state DP, okay, where you have state transition between the dynamic programming from one state to another state, you might have done that already. So if you have done that, if you have not done that, okay, no problem. You might have also studied operating system where you have job submitted, then job in the queue state, and then job in the running state, then job in the waiting state, job done state. So all these state transitions will keep happening. Schedulers are present, and it keeps. I mean, there is a short-term scheduler, long-term schedulers, and these things keep happening. If you want to do this in programming, then you can do process task using server. This is a very commonly asked interview problem. Process task using server for senior engineers, especially because this is like an operating system simulation. Process task using server using double heap. So this is a two heap approach, one min heap and one max heap. So if you have done this well and good, so in this state transition, I'm thinking in that way, going from one state to the another. What is a state vector? And how do you derive? Like if you have not understood till now, it's not a problem. You can assume state vector to be something which gives an idea of all the unknown values on the RHS. All the unknown values on the RHS is coming in the state vector. What are the unknown values or variables in the RHS? I just know about the two values, f of n minus 1, f of n minus 2. So I can write f of n minus 1 and f of n minus 2 being the two values, and this is the state vector for, let's say, s of n minus 1. Let's say I can say that in the RHS, whatever are the unknowns, you just push it. Now, if you are thinking, how do I know it will be a row vector or column vector? You can take any vector. You can take any vector, but I like to take row vector, so I have taken row vector simply. Okay, so let's take a row vector. If you have taken a row vector here, is this clear, like how I have defined this? And you will find why I have only defined two values, because on the RHS of the recurrence relation, there are only two different unknown values. There are no three values. There are no two values. I mean, there are no one value. There is only exactly two value. So if you know the recurrence relation, there will exactly be one state vector. You cannot have two different state vectors. I hope we are clear. Any question in this? No question? No question, right? Okay. So this is my state vector. Let me write it more clearly. If I have to write the simplest state vector, let me write it as f of 1, f of 2. You could have written f of 0, f of 1 as well, but let me write f of 1, f of 2. The condition according to this idea is, if I take certain, you can say state vector, and if I multiply with my magic matrix, I should go to the next state. So in my next state, if I have to write f of n plus 1, what do you think will be the RHS? Can you tell me by looking at this pattern? What should be the RHS? F of what? F of n plus
And
f of n minus 1, right? So if I have to say that you will go to the next state, so what should be that state? Can you guess here? What should be the numbers that I write? F what? And F what?
F2 and
Yeah, F of
3.
2 and 3, isn't it? This is the next state. So, I just represented your recurrence relation in the form of a matrix. I didn't do anything else. Okay, I'm not doing any new idea or something. It is just like, okay, it was written in algebraic format. I have written in matrix format. That's it. And all the unknowns are already taken in the RHS. So why didn't I take the LHS? LHS is just the function definition. Like it is saying which state it is. It is the nth state. It is n minus 1th state, right? But what it exactly contains is in the RHS. So if you compare one RHS with another, then don't you know what is the transition that happened in the value? You know it exactly what happened. So this is that state. Okay, we know about the state change. Now, after looking at this, can you tell me the dimension of M? Now your job is to tell me the dimension of M.
2 cross 2.
So first you write this dimension, 1 cross 2. This is 1 cross 2.
So first row means rows will be the same as column of the first matrix. And what is the result of the column of the second resultant matrix? That should be the column of the M matrix.
So this row, I mean, this column should be common here, and this column should be common on this side, right? You know it. PQ, QR equals PR. Okay. P times Q, Q times R equals P times R. So you know this Q and this Q should be common. So I have taken 2 common, and I have taken this R common. So this 2 is common. I know it is 2 by 2 matrix, but I don't know the content of it. It is not an identity matrix. It may be an identity matrix, I don't know, but it is generally not an identity matrix. Otherwise, it will not transition to some new value. Identity means keep the value same. So it is not an identity matrix. So can I write it in this format? F1, F2 times A, B, C, D, 2 by 2 matrix. So it is a 2 by 2 matrix. It is 1 by 2 matrix, and I will get F2, F3. Can I not write like this? I can write like this, right? Now, if you think about reducing this two into a single matrix, I should do that to compare these two. Then can you tell me, after multiplication, what will be the dimension of the resultant matrix here so that I can compare with this matrix?
It will be
1
1
by 2.
cross 2 only. And
Yeah, it will be 1 cross 2, right? It will be 1 cross 2.
hmm.
So
And
let's create the equation on multiplication. This will be multiplied with the first column. So if you multiplied that, you get AF1 plus CF2. C times F2 equals F2. And you get another equation where you have to write F1, I mean, this one, right? B times F1 plus D times F2 equals F3. Now let's compare this first equation, this RHS with LHS. You know that A will be equals to 0 and C will be equals to 1 by comparing RHS with LHS. Okay. And if you do the same for this, then what will be the value?
1 1. F1 plus F2 equal to F3.
F1 plus F2 equals to F3 due to this recurrence relation, right?
Hmm.
Because if we again start comparing, then here we cannot compare, but you know from the recurrence relation that F3 equals F2 plus F1 due to the recurrence relation. Okay. So I can safely assume B to be 1 and D to be 1. So have I found my magic matrix that I was talking about? 0, 1, 1, 1. This is my magic matrix. Okay. You can again revert back and process these things. If you have any question, you can ask. Then we will go to the next step. I have derived the magic matrix. I'll tell you about what we did. I am trying to solve the nth Fibonacci number problem. This problem is the most asked problem, nth Fibonacci number. If you get easy interview on matrix exponentiation, then you can expect this question. If you get harder interview, then you can expect the second question that we will be doing. I mean, the next question. So in the easy interview, you will be given the recurrence relation. You will know the base cases as well. You just have to find it with matrix exponentiation, which is maybe more optimal than the linear stuff that we would be doing. So in this case, you can form the exact state vector. You know how to make it. Take all the RHS and just write it as it is. You can write it row wise. You can write it column wise. It is just up to you. Only the dimension of the stuff are going to change. Nothing else is going to change. And because even if it is column vector on the right hand side also, it will be column vector. So the consistency will be maintained and you will always get a square matrix in the middle. Okay. You know why you get the square matrix? Because the row, I mean, you know why it will happen, right? We just compared here. So anyway, and after this, you know how to compare the equations and derive this. You will not write code for this. This you have to definitely do in the Google Doc or pen and paper. You should not write code for this. If matrix exponentiation question comes, you have to write the recurrence relation by typing in the doc or writing in the pen and using pen and paper. Find the magic matrix. Until you find it, you cannot code it. Okay, so we should not start typing it right away. We should arrive to a correct magic matrix. Our recurrence relation should be verified. It should be correct. Interviewer will also agree with this. You go to the next step. You find the magic matrix. He will agree with that. You go to the next step. Coding step is the easiest one because you know everything is correct. Then the code is like how we have already seen. So I hope till this derivation everything is clear. Now we will go to the last step. The last step is about find the nth Fibonacci number.
How do you find the nth Fibonacci number? What to do? So if I write f of 1, f of 2, in when you multiply it one time, you did one state transition. That means you included the next value here. So if I say that the 0th value, or without doing any kind of state transition, I was at the first step. In one transition, I went to second step. I mean the second value. So if I want to go to the nth value, how many transitions I will do? N minus 1 transitions. If I'm starting with 1 and I have to go to n, then if I have to count in how many steps I can reach, I will reach in exactly n minus 1 steps, right? Yes, Amar.
But I didn't understood this equation, like
Which one?
how f1 comma f2 into m is equal to f2 comma f3. So what is
No,
this f?
that we are assuming. That we are assuming because in
How did
every
we assume it is f2 and
so there
f3?
is a proof for it that if you have a linear recurrence relation, then you can solve it with matrix exponentiation in this given format. So we are not interested in that proof. I am
No,
saying that.
that is fine. Like, yeah, we do not want to go into the proof, but so above it, we say s of n minus 1 into m is equal to s of n,
Okay.
right? So below it, how we know that f2 comma f3 is s of n?
Okay. I'm not saying it is S of n. I never said that it is S of n. I'm saying that we are going to the next state. So if you take this as S of 1, then this is S of 2. If you assume it to be S of I, then this is S of I plus 1. That's it. I'm
Okay,
saying we are going only to the next step.
understood. Okay.
Okay. Yeah. So now that you have understood all these things, matrix, I mean, multiplication, binary exponentiation, everything you have understood, and how to find the magic matrix. Then if you multiply the magic matrix with the f of 1, f of 2, you must transition to f2, f3, and let's verify our hypothesis, isn't it? Let's verify our hypothesis. So what is f of 1? 1. And f of 2 is also 1. So let's multiply with our magic matrix, which was 0, 1, 1, 1. Yeah. So 0, 1, 1, 1. Can you multiply and give me the result, what it is going to be, and not just add the value? So it is going to be 1 multiplied by 1 plus 1 multiplied by 1, which is 2. And 1 multiplied, I think it is.
It should be 1.
1, 2.
Okay. I just read this as 1. So it is
1
0. And then 1 multiplied by 1, this 1 multiplied by 1 and 1 multiplied by 1. So this is going to be 2. And in the Fibonacci series, F0 was 0, F1 was 1, F2 was 0 plus 1, F3 was 2, which is 1 plus 1. So you know that we have made this transition from F1, F2 to F2, F3. And if it is running, then your magic matrix is correct. It will always be correct, okay? You don't have to check it. So always remember that the proof only exists for linear recurrence relation, not for anybody else. I'll show you other type of recurrence relations too. It is the most basic one. Okay. So, yeah. So I think we are good with this. Now I'm trying to find how to go to the nth step. And you know that if I start with 1 and I have to go to nth step in step size of plus 1, plus 1, plus 1, then I have to do n minus 1 time transition. So in matrix exponentiation, it says that if I just calculate to the power n minus 1, then I will be reaching to the nth state. From f1, f2 to I will reach to fn plus 1 in n minus 1 times transition. So if I write this 0, 1, 1, 1 to raise to the power of n minus 1 multiply, I will reach to this state. So what I have to calculate here? I have to calculate this matrix, magic matrix raised to the power of n minus 1. That's it. I don't want to do anything else. And what will be the dimension of this m to the power n minus 1? Can you tell me?
2 cross
No,
2.
it will be 2 cross 2 only, no?
Yeah, it will be 2 cross 2 because the same matrix is multiplied by the same matrix. And that's how the code was also written. This code is about multiplying the matrix with itself, where I have assumed D is the dimension because it is a square matrix, and then this entire piece of code will run. No problem. Now, how do you calculate m to the power of n minus 1? I already told you how to do that. Our next step is about doing the live coding, that you will be telling me what to do and you will be taking out the laptop and doing it as well. So how to do m to the power of n minus 1? Just the exact same code. That's it. Nothing else. With this, you have to write the matrix multiply. So maybe your head is rotating left and right. So let's open a lead code problem and let's try to solve it. Yes.
Sorry, Surya, I did not understand this equation here, F1, F2, and then we multiplied with the matrix, a magic matrix raised to the power n minus 1. How did we get to this?
Okay. How did we get to this power or something else?
The power, yes, n minus 1.
Okay.
Yeah.
So we were saying that this, I mean, now again, Amar had asked about how did you assume it. So this came from a proof that if you have a linear recurrence relation, then you take a state and multiply with the magic matrix, you will go to the next step. Okay, now the next step is to find the magic matrix. So we found the magic matrix as well. Now you have to pick where I should start. It may not be F1, F2. It can be F0, F1. Then I have to do one more power transition for this M. Maybe. Okay, so it depends like where you start. Whatever value is available with me, I will start there. I can also start from F5, F6. Why not? But you have to calculate F5 at F6. You have to have those values, right? So why did I do F1, F2? Because I have those values, F1, F2. I also have F0, F1. So I could have started there, but it will take one more step on your M. Why I'm assuming only this value as the answer and not the last value? You can assume the last value and do one less step as well. So it is up to you how you solve it, right? And how did we arrive at this n minus 1? Because we were starting with first state. That's what I'm assuming. And I have to go to nth step. So each of these power will define how many state transitions you are doing. So if from 1 to n you want to reach, then in n minus 1 state transitions you will be reaching. In one, if you add n minus 1, then you get n, isn't it? Yeah. So that's how these values came.
Okay, thank you.
Okay, so let's open problem number 509 and let's see how you solve it. What is the time complexity? First, you tell me the time complexity of this. Or maybe after writing the code, we will see about time and space. Okay, after writing the code. So let's open the code. Are you guys opening in your laptop? Because you have to open in your laptop and you have to also code it.
Yeah.
Let me stand up because I'm sitting a lot. Remove my keyboard. So now we can start coding. Let's start. 509. You please open 509. Okay. I see that there are less people today in the class.
You scared everybody, Surya.
But you guys said that you want to prepare for Google's interview, right? What to do?
I know.
And this is a very common problem. It is not even a problem that I will say it occurs 1 in 100 times. It occurs more than that. It has different format. The easier question comes for the SD1 role, like L3 roles. But since you will not be appearing for L3, you can expect more difficult questions. But if you know, I mean, it is just like remembering the stuff and doing it. It's not even like you have to apply your brain, think, derive, nothing like that. It will be standard problem. There are only 2, 3 standard problems that comes. One of them is going to come. That's all. Yeah. So is my audio good or what it is? How it is? Okay. You see this
Yes.
problem. This is a recurrence relation. Seems like it, right? What do you say? Seems like a recurrence relation. I hope my audio is good. So
Yes, sir.
yeah,
Audio.
please start writing the code, or should I write and you will tell me like what I should write? Yeah, you tell me what I should write, or you type side by side. You type side by side. I think then we can submit together. That will be a good
No, I'm
achievement.
writing.
Yeah, you guys also, everyone start side by side. And if you
I'm
miss
writing.
somewhere, then we can also, you can look at my code as well, like what I'm writing. So first of all, where should I start? Fibonacci number of n. And you see the constraint first. The constraint is only till 30. What is the 30th Fibonacci number? Like if you are thinking, oh my God, I might overflow, then you use long integers. Okay. So I will be using this because I don't believe anything else other than long integers. So I will be doing that. And let's take care of the base cases initially. So f of 0 is 0, f of 1 is 1, right? So if, I mean, where I'm writing, yeah, if n is less than 2, n is less than 2, then what should I return? N should be fine.
Yes.
Okay. Yeah. Okay. First step clear, the base case taken care. What should be the next one? I should define the magic matrix. Now I said that in matrix exponentiation, you must have already derived the magic matrix. What was my magic matrix? 2 by 2 sides.
1. Yeah.
Yeah, 2 by 2 sides. And what were the values? 0, 1,
0, 1, 1, 1.
1, 1. Okay. 0, 1, 1, 1. Okay. So this is your magic matrix. Let me write magic matrix. What to do as the next step? How many steps I have to do? N minus 1 steps I have to do. So what I need to calculate? What is my initial state, first of all? Initial state. Let's call it f of size 1 by 2. And what is that? What is f of 1? It is 1. And f of 2 is also 1, right? So let's go from f of 1, f of 2 like that. Is this fine? Initial state? F1 comma F2. Okay. Yeah. I hope you guys are typing. Okay. If you have 2 screens, then it's good. Then what to do in the next part? What do you think? I should be, I have to calculate f times m to the power of n minus 1. Then let's calculate m to the power of n minus 1 and then multiply with f. Matrix multiply. So I have to write 2 code. One code matrix multiply, one code binary exponentiation. So let's write it. So I have to do binary exponentiation. And what should be my power? It should be m to the power of n minus 1. Okay, fine. So if I have to give the comment, then find n to the power of n minus 1. Fine. So let's write this. Do we need to return anything, or we will be doing it by pass by reference? Let's do it by reference. It will be cleaner. Should I write base exponent of these values, or how should I write? I think I should define LL for everyone. Let's keep LL. Even though you write integer, I think it should work. But let's write the long integer. So let's keep the value as m, and then let's keep exponent. Even though you could have write base and exponent, that would make it more readable, isn't it? So let it be m, whatever it is. Okay, please tell me what to do first. For finding binary exponentiation, we have to handle two cases: even power, odd power. For odd power, I have to multiply with the result. The result will be initially an identity value. Okay, so let's define the identity matrix. And it should be result of size 2 by 2. And I can actually define the value as it is 1, 0, and then I can give 0, 1 as the identity matrix. For larger one, you can write for loop and you can do that, but let's do it in this way. Then let's create a base variable. Okay, because this, if I assume m to be base, then base will always keep changing. Square the base and half the exponent, right? But I don't want the m value to change. M value will only change by assigning it with the result at the end. Okay, you will understand after writing. Let's take a base. Base will be the same size. And what will be the value of base? Exactly the same as the matrix. So let's say m at 0, 0, comma, m at 0, 1. Are you guys writing? Where it is from? M at 1, 0, comma, m at 1, 1. Okay, I think it is correct. 0, 0, 0, 1, 1, 0, 1. Fine. So it is a small example, so I'm just assigning everything without loop. Okay, so I have created this. I will be changing the base, square the base, half the exponent. Okay, let's try to do it. So how to write the code? While exponent is greater than 0, or you can also write while exponent. What should be the first line? If
exponent
is
and
odd.
percent 1.
If the exponent is odd, then what to do? Matrix multiply. I will write the code later, but let's say matrix multiply. You have to multiply the result with the base. Result with the base, that means your 1 power of m will be stored. Okay, result with the base. Now, why I'm doing base? Why not I'm doing 1? Because base will keep on updating. Because maybe initially you were not seeing a power of, let's say, odd number. Like if you started at 2 to the power of 14, then you will reach to 4 to the power of 7. Then at this point, you should be saving 4 to the power of 1, isn't it? 4 to the power of 1. So you should take the updated values power 1. Who will update? The base is only changing. I will not touch m until I get the final result. Okay, so if you are thinking why I didn't write m here, like m to the power 1 should be saved. No, it should be the transition state. At whatever state you are, that power 1 you have to save, isn't it? At this present state, 4 to the power 7, your base is 4. But your m value is always 2. Okay. I hope we are clear. Okay. So what should be the next step? Exponent minus minus.
Even if you don't do minus minus, next time when it will divide, it will be
it
handle
will take
that.
care, but let's do minus minus. Because odd power will be lost when you divide it. But let's keep it clean and let's do a subtraction, minus minus. So what should be the next step? Square the base and half the exponent, because now you know that it must be even power. In line number 17, when you reach to line number 17, whether you hit the if statement or you didn't hit it, in either case, you will find that at line 17, your exponent is even. Right? Your exponent is even.
Matrix
So
multiply
what should I do?
Just multiply that what m you have taken now, so m will become resultant. Sorry, we will.
So matrix
M will
comma
become
base.
multiply m comma m.
multiply.
M comma m.
Base comma base.
Base comma base.
No, base comma base. Yeah. Base comma base, because base is the current state of the base.
And
M
power
was the initial state of the
exponential,
base.
just do left shift or
By one time, isn't it? And this will actually give me in the result, I will have the final state. But you see that I'm using a void function here. If I was not using void function, then I will be returning the result directly. But I'm using a void function and I'm willing to store the final answer into M. That means what I want to calculate is I wanted to find m to the power of n minus 1. So the final value should be m to the power of 1. So m should have the changes. It should show the changes in the main function in this Fibonacci function, right? So if it has to show the changes, then I will have to copy the result into m, because result has the final answer, right? If you have done binary exponentiation, you know it is the same code. So result has the final answer. So in this case, I cannot return the result because that is not what I'm doing. You can do that and you can receive using a 2 by 2 matrix, but I will be just copying. So what will be the value? Can you tell me what will be the value? M at 0. You can use for loop, but I'm not doing for loop here. M at 0, 0 equals result at 0, 0. M at 0, 1. Again, if it is larger, then you have to do for loop. Result at 1, 0. Okay, I think so. We are done with this. Transferring the change from result to M. I hope it is good. Then after that, what should I do? I should write this utility function matrix multiply. How many times I have used matrix multiply? 2 times. Now you see what type of matrices we are multiplying. We are multiplying result with base. They both have the same dimension. We are multiplying base by base. They both have the same dimension. I don't care about the value, but I care about the dimension. So every time I'm multiplying, it is the same dimension, which is a square dimension in this case. So I can hard code it even. I don't need to pass the, you can say the value. So I think I have written matrix multiply, right? So what should I return? Should I return something or should I just keep the changes? Let's keep the changes. Are you guys typing? Okay, so I'll keep writing this integer all the time. Okay. So yeah, let's do it. Long type or integer type? I think I have defined long type. Yeah. Okay. So what I need is 2 matrices. The first matrix is going to be, you can say M, or let's call it A. Should we call it A or M? Let's call it M and B, because I don't want to change the names. 2 and 2 size, and I have to take B, 2 and 2 size. Is that good? Okay, I'm hard coding all the values. So I don't see anyone. Everyone went somewhere. What happened?
Here only.
Everyone is typing, turning off your videos. Okay, let's keep the result in result, even though the name looks to be same. You can take some separate name. Let me take result only. You can take multiply or anything. Just don't take the same name on all the functions. Then what should you do?
Take ABC now
ABC?
for matrix
Correct.
multiplication.
Let it be M because I want to see that it is the same M which will be reflecting at the end.
Okay.
Okay.
So we will run one loop from I equal to 0 to I less than 2. I plus plus, and second loop will be j equal to 0 till j less than 2.
J equals to 0 to j less than 2 plus plus
J
j.
plus plus j, and then
Okay.
third loop k we will
Before
start
the
from
third
0
loop, I
and
will be assigning multiplier ij equals
equal
0
to,
so
yeah.
that it does not go into some garbage value. Then I will have the k type.
Yeah, k equal to 0, k less than 2.
This is the same code that we have
Yes, that,
discussed, right?
yes.
So multiplication at I
Ij plus equal to m,
ik
no,
ik ik
not,
times.
okay, multiplication ik, m you have to take, no?
Oh, I'm taking the same.
Mik into
B times of
k into j, bk or bkj,
bk.
j.
Okay. Fine. So have we found our result by this? I think it will be stored in the multiplication. This multiplication line number 5. Now I have to transfer it to M so that it reflects back in the binary exponentiation code, right? So what I have to copy it. So you can apply the assignment or you can use a for loop. So let's use a for loop. Then in which part I was going to do M at ij was location at ij. Okay. Seems correct only, right? What is
correct? You are returning, but you have to return
oh
value.
okay. We
Yeah, you
didn't
have to
return the
return the
value.
value
It did
also,
not
no?
run. Yeah, we didn't return the value. So till now we have done the binary exponentiation. So we have found m to the power of n minus 1. But I have to multiply f with m to the power of n minus 1 to get the final matrix, isn't it? Do you remember? We have found m to the power of n minus 1 by this time. Where is that transition state? So we have only found this m to the power of n minus 1. We have to multiply with the initial state to get to the final state and return the first value. So we have to do one more time multiplication. So how to do that? Where should I store? Let's store it in answer. And that is of size. What should be the dimension?
2 cross 2. No, sorry. Answer is there, no? So it will be
1 cross 2.
1 row and 2 columns.
And should I assign with certain value? Let's assign it with 0 because it is going to compute and store values. So
Okay.
last time I was assigning 0, 0 before
Mm.
doing the calculation. This time I can just do it without for loop because you know how it is going to go. Let me show you. So yeah. So it is going to take these two values, multiply and add with this. It is not 0, 1 and 1, 1. It will be some value. And then take this same row and do it with the second column. That's it. So it is constant operations, small matrix. So I don't need to use loops, etc. I can just do it as answer at, you can say 0, 1 will be equals to what? Initial
0, 3.
matrix.
First
Initial matrix
column.
was F. F
Mm.
at 0, 0 multiplied by
M
M
of
at 0, 0.
0, 0.
Top left corner plus F of 0, 1 multiplied by M of 1, 0. Isn't it? If you think what I have written, then I'm trying to just multiply this F1 with this value and F2 by this value and add them.
Oh, yeah, correct. So
Okay, so
F1, 0.
that will be this Fn value.
So that will be 0, 0. No, you have written 0, 1.
Actually, this should be the answer. I should not even save it anywhere. This should be the
Okay,
answer.
you're directly calculating the answer only. You're not calculating entire answer matrix.
Yeah, why should I need to do that anyway?
Okay.
So I can
Return.
simply return this. I mean return what I'm writing. Maybe you have to do cast. If it is long and you have to do integer, you may have to cast it. But let's see. 0th value should be the answer, right? Yeah. 0th value is the answer. Okay. So I think if you do with this, it should work. And have you guys done the typing? You all
I've
have done it.
written one code. I've pasted in the text. There I have taken 1110 matrix. Here you have taken column matrix. There I have taken row matrix.
I have taken row matrix, right?
No. Okay, you have taken row matrix. I have taken column matrix.
Okay. So you guys are done with the code. Who all have done can raise their hand. And if we need to wait, we will wait some time. Yes, guys. I need more videos turned on. What is happening? Today, I think internet is not running well, or what is happening? Yeah. So have you guys typed it? Take your time and type it. Because if you type it, then a lot of things will get clear, you know. Yes, Soumya, have you typed it?
Yeah, no, not completed yet.
How many functions? Which function you need to see? You can also see and type. It's not a problem. You should understand and see and also type. No problem.
Surya, I have
Yeah.
one question.
Yeah.
Can you explain this line number 23, how we declared this base matrix?
Okay. This base is equals to M. Exactly the same. So I'm just copy pasting it. But you cannot just directly assign here in C++. If I think in Python, you can directly assign. So you can directly assign it. But here I have to do, each cell I have to assign.
Okay.
It is the exact same thing. So anyone has any confusion in anything? I have shown you each of the part by breaking down, but still if you have anything to ask here.
Here you have taken row matrix. That's why you have to multiply in the last also. If you take now column matrix, we don't have to multiply in the last because there the first term will be 1 0. So that will be 1 0. So even if you don't multiply, you will get the correct answer in the F,
Okay.
in the M.
Okay. So how many of you are done submitting the code?
Yeah, done.
Done. Nice.
Mhm.
So 2 of you guys are done. Waiting for more head count. 3. Okay. If you need to understand any line, then please ask. Soumya, you want to ask something, or you were saying that you are done?
Done. Sorry.
Okay. Um,
Peter, one question. Again
yeah.
on the base matrix.
Huh?
Do we
Regarding.
really need to declare this base matrix? Can't we use the M itself?
But that M will change. If you are good with that, then you can use it. The M will change.
Oh,
I
because
mean,
you're
I
passing
can,
it
if
with
I
the
if I don't
proof.
care, I
Hmm,
can use it.
I
If I
get
don't
it.
care, because in this case, if I take M, uh, then I don't think I'm using it anywhere else, right? And even in the
Hmm,
final portion, I'm not using. You can also change M. You can try to do the changes if not needed. I just separated it.
got it.
Okay, guys, we have to do little faster. We have more problems. Or you want to do part 2 of this? So just wanted to remind you that this is the last week we are having 2 classes in the weekend. From next week, we will be having 1 class that is on Saturday at 10 in the morning. I'll post it in the group.
Ten a.m. IST?
Yeah, 10 a.m. IST. You are in EST time, right?
Yeah, EST.
So it will be night for you. So it's good, right? Friday
Yeah,
night.
everything works.
Okay, guys, I'm not seeing any reply. What is happening? So let me count.
Scroll up a little
Chandan, are
bit.
you done?
Can you scroll up a little bit for matrix multiply function?
Okay.
That's the one.
Vidhi, I think you are having a dinner.
No, sir. No, sir. I'm trying to solve.
Because because you are not to be seen from the past 10 minutes. So I thought you are in some other agenda.
No.
Okay. So, Vidhi, are you not done with this?
Yeah, it's giving me incorrect answer.
Incorrect answer. You match line by line. Something will be wrong somewhere.
Yes, sir.
Or should I share this code in the group, in the WhatsApp?
Yes, because I'm doing in Java, so I think I must have done
Okay.
something wrong.
Okay. Then maybe you can check later. I think so. We should proceed now, isn't it?
Yeah.
Yeah,
So,
we should proceed. This recording will also be present anyway. So let's go to the next problem, 1137. Let me open 1137 now. That is the same. It is Fibonacci. This problem I haven't solved, but I know that it will be solved with exponentiation again. Because how do you know it is exponentiation? It is given recurrence relation, linear recurrence relation. Right? If you ask me like, how do you know? Then let me show you. This is that recurrence relation. T of n plus 3 equals Tn plus Tn plus 1 plus Tn plus 2. If you just take this one, it will become the Fibonacci. If you take one more term, it is the Fibonacci. Now, my class work here to you is find out the recurrence relation. Sorry, the recurrence relation is already given. Otherwise, I would have given this. Find out the state vector. Tell me what is the state vector, which is Sn times, or S1, whatever I write. Try to find in Sn minus 1 terms. Magic matrix equals Sn. So I want you to find the n minus 1th state vector. Second thing, I want you to find the magic matrix, because these two things are needed before writing or thinking about coding. So please do that. See this. You have already done the Fibonacci, so I'm expecting that you can do this. So I'm giving you 2 minutes of time. I think that should be enough. If you are not understanding where to get started, then I'll tell you where to get started. So you know how the recurrence relation is written? Tn plus 3 equals Tn plus Tn plus 1 plus Tn plus 2. Okay. If I'm telling you to write in terms of n minus 1, n minus 1th term, then you can convert it to, let's say, n minus 1 or n, and you write it as, you can write it in any order, right? What is this n plus 2 anyway? It is just the last term, n minus 1 plus n minus 2 plus n minus 3. The last three terms, when you add, you get the current term. So if you have to make a state vector, how many values will there be? 3 values. Okay, so if I write T1, T2, T3, it will be T1, T2, T3, isn't it? And if you multiply it with the magic matrix, which should be of certain dimension, which I'll tell you what will be the dimension, you should get one transition, T2, T3, T4. If you ask me, how do you know it will be one time transition? Why not 2 times transition? Why from T1 to T2 only? T2 to T3 only? Because you have to calculate each of the term incrementally by only one step. You cannot calculate by 2 steps, because for any nth step, you need 3 results, and the closest one is n minus 1, and the minimum gap between them is only 1. So you have to only go at one step. You can't go with more size jump. It is not possible. And that is why our transition will also be 1 step. Okay. Now this is 1 by 3 dimension. This is 1 by 3 dimension. You know what is this going to be? Isn't it? 3 by 3. Isn't it? It is going to be 3 by 3. So let's assume this to be A, B, C, D, E, F, G, H, I. Now what will happen? You compute these values. You compute what is T2, what is T3, what is T4 using these multipliers. So I'll tell you one, you can say A times T1, A times T1 plus D times T2 plus G times T3 equals T2. Now, is there any relationship that you can actually establish with T2? I think so. You know, T2 is 1. And you know that this T2 and this T2 is the same here. So what is going on is A should be 0, isn't it? A should be 0, D should be 1, G should be 0. These are the values that came up. A0, D1, G0. So if you put D1 and these all should be removed, then you will get T2. This is how you can compare, isn't it? You can apply any kind of comparison, but I think it is straightforward. So you can compare like this, and I got 3 values. So if I have to build the magic matrix now, I got these 3 values as 0, 1, 0. Let's go to the next equation. So what is the next equation? B times T1. B times T1 and go in the same column plus E times T2 plus H times T3, and it should be equals to T3. Then you know the values. You know B and E are going to be 0. Where is B and E? They are going to be 0. And what is H? H is going to be 1. Is it fine? Let me check my notes. Yeah, it is fine. It is fine. So let's go to the third one. C times T1. Are you guys understanding how I'm finding? And how did I even arrive to these kind of representations? F times T2 plus I times T3 equals T4. Okay. Now in this case, T4 is not present, but you know this recurrence relation, isn't it? You know the recurrence relation. If you have to represent in terms of T4, then it will be the sum of T1 plus T2 plus T3. So T1, T2, T3 are already there. So C, F, I are all going to be 1, 1, 1. Okay. This is my magic matrix. I found the magic matrix. What should be this value? T1, T2, T3. I think so. You can calculate 1, 1, and the next one is going to be 2, 0 plus 1 plus 1. So I can write it as, where should I write it? 1, 1, 2 multiplied by my magic matrix, which is going to be 0, 1, 0, 0, 0, 1, 1, 1, 1 raised to the power of n minus 1 equals, what should be it equals to? T what? N, Tn plus 1, Tn plus 2. If you want to do less times n minus 2 times, you do that, you will get 1 time shifting on the left side. I mean, just shift the value. If you do n minus 2 times, you will get Tn minus 1, Tn plus 1. That's it. So it's up to you what you want to generate. But let's go with the standard approach. And now what you want to find? The next step, matrix exponentiation on this to calculate the final 3 by 3 matrix. Then you do matrix multiply here, get this matrix, return the first value. So this can be a good practice problem having done the last problem. It is the same problem. Okay, so let's not give time to it. Let's go to the next problem. Because these two problems were easy problems. Here the recurrence relation is already given. Right? Recurrence relation is already given. So let's go to problem number 790 unless you have any question in this. You have any question in this?
Sir, one minor question. Here
Yeah.
you assume A should be 0, but T1 is also 0. So anything we multiply with 0 will be 0 in the first equation.
Which one? Which one? Which first
AT1,
equation?
AT1 plus
Ah,
DT2.
okay.
Yeah, so the
This one.
T0, okay, T1 is 1. Okay, my bad. Yeah, so that's why we took A as a 0 to get 0 as an answer.
Yeah. Okay. I think you understood without explaining. I didn't get the full question, but I think you got it right.
Yeah, I got it.
Okay. So, yeah, I mean, I think it is simple if you have done the last question, right? So let's go to the
Yes.
next question.
It
I hope
worked for
that,
me in Java. Yeah.
yeah. So you can also come to this part of the video and get this entire stuff and just check it, double check it if it works
Yes.
out, right?
Yeah.
So let's go to 790 because 790 is the design problem. That is the problem that senior people can expect. If you want 1 CR package, 1.2 CR package, then that is the question that you can expect, right? This is not for L3 roles. For L3 roles, generally people will not harass you so much unless you want that 1 plus CR. Now, I think you are good to go. So for somebody like Sandeep, that Fibonacci and Tribonacci is good enough. Okay. So I have pre-coded it because coding it will be pain already. Right. We don't have time also. I knew that we will be running out of time. You see, it's already 9:21 and we haven't even understood what happens if constants comes and this and that, right? So I have to tell you that too. And I have to finish before 10 because I have another meeting actually. So let me see. Okay, before solving this, let me just tell you about some more things like how to convert some more complex equations into matrix format, isn't it? Because we have just seen the simple linear recurrence relation. Okay, I'll come back to that problem. But we are not going to do assignment or discussion on this topic because already we are doing everything in class. So I expect that you can do it, right? So before that problem, I want you to find out two things, state vector and magic matrix. Whenever I'm giving a problem now, you have to find it because I'm expecting code is going to be same. Once you have found out the things, the code is going to be same. I want you to find out the state vector and what magic matrix. If you want to understand what is state vector, then S of n minus 1 is your state vector for n minus 1th state. Multiply it with m to the power of 1 and you will get to the nth step, which will fetch you the result. So for doing one transition, you have to multiply one time with the magic matrix. So if you get this one and if you get this one, then you can get the nth step as well, right? So this is your state vector. This is your magic matrix. These two are the ones that I am asking you to derive. So let me give you different type of equations. And then you will understand what is the recurrence relation and what do I mean by that. F of n equals 2 times f of n minus 1 plus 3 times. Now this is this example is a pretty standard example in matrix exponentiation. So I am also giving the same standard thing. F of 1, f of 2 is given as the base cases. Problem can have any kind of story. I don't care what the problem story is. But if this is what is given, or you can think that it is given in such a way, like what if I make the story without writing it even? Like let's say this is not even written. And I'm saying that, there is a special game called, let's say, Google's AI game. And in this, I will give you some bunch of stories. And I will say that, in this game, if you want to maximize your profit, if you want to go always make an optimal move, then you can always do that by looking at, 2 times f of n minus 1. If you look this value and you take 3 times f of n minus 2, then you will be able to make maximum profit, or you will be able to make such a move in your board so that nobody can cut you or nobody can damage you, or you can score the highest score with maximum safety. So your brain should not move around the story. The brain should be thinking about, okay, it is saying that if you just get these two values and sum them up, you will get a certain value where your next move should be to this cell. Then again, your next move should be defined by these two previous values. Have you understood what I'm trying to say? I'm trying to make up a story, some kind of AI game. You are fighting with the AI. You are the player, player versus player, PvP, or player versus the PC or the AI. In any of these cases, you can always calculate where the next move should be depending on if you get these two values from the past states. So most people also get derailed because they are not even thinking about the recurrence relation. They are just thinking about the story. Too much, committed to the story. Whenever a story comes, then you should think that why stories are given in the test. It is given because just to lure new people into this, so that your mind do not run around array, your mind do not run around these patterns, isn't it? And then people say that I can't solve the story problems because you are too naive to think that this story is only to get you inside. Your brain should not be occupied in the story, but still you are getting occupied. So you know what to avoid, or you have to always look at the numbers. You have to always look at the data structures. Okay. So I have given you the warning. Now it's up to you. Right. So please do it. Can you tell me the state vector?
Yeah, but I have written column wise. So f of n minus 1 is equals to 2310 to the power n minus 1
No, I
into
don't want the value. I want just the state vector.
2310 I have written, but
No,
in
I
column
don't
wise
want the values. I want the variable names. What you have written?
it means it will be 2 cross 2 matrix.
Let's. No. State vector, right? How it will be 2 cross 2?
Okay,
If
state vector is that is here you have written s of n minus you have written.
if you
So
write column vector, then there will be two values. If you
so
write
2
row
cross
vector as well, you have
1.
to. Right?
So it will be 2 cross 1 f of n minus 1 f of n minus 2.
Okay. So, I mean, as an initial step, yeah, you can write like that: f of n minus 1
f of n
and
minus
f
2
of
into
n minus 2.
into see f of n 2 and 3. So in 2.
Okay, let's not talk about this right now.
Okay.
Let's not talk about this. And your result should be shifted by one time. So
So f
I
of
think
n minus 1.
I think my representation here is incorrect. I should write in a proper order. Otherwise, the result will also occur in that order, right? So I should
Okay.
write n minus 2, n minus 1, so that I can write here what? N and
n minus.
n plus 1, something like that.
Okay, you are taking n
Depends
plus
on
1.
how you
I'm
write it.
taking n minus 1. Means basically 1 you have to increment.
Yeah, so this I am taking it as s of n minus 1.
Okay.
Okay, s of n minus 1 will give me s of n minus 2 and n minus 3. So this is s of n only. There's not s of n minus 1. But anyway, whatever is the case, I don't care. Let's start here. I can start with some kind of initial value as well. But let's see the state vector. The state vector in the column format will be simply f of n minus 1 and f of n minus 2. So in the RHS, whatever are the unique terms, you just take it. These constant multipliers will be ignored.
So
What if you had this n? 5 times n. Then what would you do?
then we have to, okay, n minus 1 times we have to multiply this n also.
No, you just have to take n. You just have to take n.
Because this value are only getting replaced. That will be constant.
Yeah, and if there is 5, then
we have to take 5 only.
no, then you have to take 1. So if there is any constant that does not change, you have to take 1. If you have a function, you take that function. Now this is kind of a vector. It is not a function. It is a scalar vector. It is called scalar. If you have a scalar, you take that scalar.
Okay.
Okay. Yes. These are some.
Why we are taking it in a column way, like not in a.
I mean, you can take in any way. Like he was doing column, so I'm taking. I am now doing column. So suddenly I'm shifting from column to row, but you can do in any way. Column looks better for more variables. It's easier, like you don't have to put commas and right? Top down. It is easily readable in the column format. So you can do in column format. But while coding, it is good to write in the row format because it is easier to do so. If you create column, then inside a box, you have to always make one more box. So that can be painful, right? So while coding, I do row wise, so that's why I was doing row wise here. But he was doing column wise, so okay. Column wise is also fine. Okay.
Okay.
Now I need you to find the dimension. This is 1 by 2. I think you are now used to this, right? This is 2
2
by
cross
2.
2.
So you know if it is ABCD, can you please derive the values of ABCD?
Yeah.
I will just match this time with the final value. I don't want to find it myself. I have already found it. You guys match with my answer. Uh, I mean, I should write some starting value, right? Like let's say f of 1, f of 2. And then you multiply with ABCD. And so you get f of n plus 1. And how many steps will you do? N minus 1 steps. So yeah, can you please find the now that we know this, because without knowing this, we would not have reached here. So once you have determined the state vector, which is this one state vector, then you know the magic matrix dimension. And now the second step 1 done. Step 2, find out the magic matrix. After this, you can apply the code. And you know, in matrix exponentiation, all the code are same. You can just copy paste the code, keep copy pasting, you will get the same answer. It is just these 2 steps. Identify the state vector and find the magic matrix in your notebook. If you found this, then rest all things are same. Yes.
Surya, so I understood this this one. This is the one that I have a problem with. How did we come to this and
How
this?
did we come to this? Okay. How
This
did
one
we
is
come?
the second one is the second one I get it with F1,
So
F2,
did you understand how did
F1.
we come to this one?
Mm,
In the
no.
RHS, like there is only one recurrence relation here, right? I think I have to do one more class in this. So we have only one recurrence relation on the right side. Okay. Using this recurrence relation, if you see what are the variables, unique variables, there are 2 unique variables, fn minus 1, fn minus 2, right? So you have to write it. Now, if I write it, I generally prefer writing in increasing order. So in increasing order means the lowest value here, fn minus 2 and then fn minus 1. Okay. So that I know if I transition by doing plus 1 state, then this will become fn minus 1 and this will become fn, right? So it makes writing easier. So I should write in incremental order. You can also write it in jumbled format. I'm not saying that you have to write in incremental order like F1, F2, F3. You can also write F3, F1, F2 or whatever. But you should also keep that in mind that in the final answer, if you have got 3 things, A, B, C, then B is the smallest state. And the second one is this and the third one is this, right? In whatever order you have written in the beginning, same order you are going to get at the end. So wouldn't it be advisable that you write in this format F1, F2, F3 so that you know that whatever you are going to get ABC state or FN state, you will get Fn plus 1 and you will get Fn plus 2. So it becomes easier to think which value is what. But I'm not saying it is the only way. You can take whatever order you want and you will still get the answer. But while picking the final answer, which value you should pick can get difficult unless you understand entirely where what answer is lying, what is the order of the answer, right? And your question about how did we come to this, is this clear? Like this one? It is
Yes.
in the RHS, what all are the unique values? N minus 1, N minus 2. So that's how I have written. You can write decreasing or increasing order. It's good to write any order. I write increasing order. You can go for column or row wise or column wise. I go for row wise because it's easier to write the code in that way. The column
Okay.
wise is easy to understand in theory. Yes.
Okay, and then we multiplied it with the magic matrix,
Yeah.
and then on the
Yeah.
right hand side, we arrived at
One state
Fn
transition.
and Fn
Yeah.
1 plus
Yeah.
1.
So yeah. Yes. I mean, it should be like if you multiply it, one time, then it should not go to this state. It should go to Fn minus 1 and
Yes.
Fn. That's it, isn't it?
Yes. Yes.
Yeah. Okay, so that was your question. Okay, fine.
Yeah. I mean, yeah.
Okay, I just
If
wrote
you.
it randomly. I was not
Oh,
even
okay.
thinking
Okay.
of that.
Okay.
Okay.
Got it. Thank you.
Sir, I have one question.
Yeah.
Initially, you explained that in this equation, if we add plus 5, then we
Which
need
iteration?
to, in Fn equal to 2Fn minus 1 plus 3Fn minus 2. If we add plus 5 to this equation, recurrence relation.
Then you have to add a constant 1 to accommodate for the constant, because in every multiplication 5 times something will get added. You have to add something for that, compensate for that with 1.
Okay.
But let's not get to that. Let's find for this one.
Yeah.
Then
So
I'll
in
give
this
you.
case,
Uh,
as F1 is 0, we have to take.
no, I am asking about magic matrix.
Yes, yes. So
Only the
there
magic
is a
matrix.
0. I think
Hmm.
3, 6, 9, 12. 3, 6, 3, 12.
No. It should have a first value as 0. Magic matrix.
Why?
Either I have done mistake or,
I
but I have
haven't.
double checked it already. It is no mistake. So
Because,
if you tell me, I will derive it also. So let's
yeah,
try to derive it, right? I think so. We will need one more class. I was hoping that today we could finish, or maybe we can finish today. What do you think? But we have to make the class longer, because in January we have 4 classes. December is the one where we have to pick up most of the things. Uh, hmm. Let's see what you were saying. So calculate the ABCD. Okay. What is f of 1? 0.
0, 1.
Okay.
Yeah, then
Let's do it in f of 1, f of 2 format. Okay. I have already written it. Why I'm writing it again. And let's do it in this way. F of n minus 2, f of n minus 1 going to n minus 1 and n. Or you can also do f1, f2 to going to f2, f3 by doing one-time multiplication. So this is not n minus 1, it is 1 only. Okay, so one-time multiplication. So can you do that? A times f1 plus c times f2 equals f2. Then a equals to 0, c equals to 1. Okay. Then you have b times f1 plus d times f2 equals f3. So what is f3 here? You find f3. F3 will be equals to 2 times of f2, which is 1, plus 3 times of f1. Okay,
into 3.
which is equals to 2. So this is equals to 2. Where is that? F3 is equals to 2.
N minus.
Okay. And how it is related with this? I think you can directly compare 2 and 3, right? Why I'm even doing all these things. You can directly compare 2 and 3. Otherwise, you cannot find it. So this n minus 1th term, that this d is going to be 2. And n minus 2th term, this this b is going to be 3. So you have 0, 3, 1, 2. Right? 0, 3, 1, 2. Yeah. Right? Yeah, fine. So you know magic matrix, you know the initial state values, which is 0 and 1. And now you find n power n minus 1, multiply and get the value. That's it. So this, whatever story it is, if you can find the recurrence relation, you can solve it. So let's go to the next problem, which is not the next problem. I have more problems for you. I think so it's better to do the next question on the next day, because it will take some time. It will not be simple. Or if you want, I think so you have already done the DP solution for that, right? Huh? I think you guys have energy now, so we can go ahead. But I have session at 7:30 and at 9 too. So that's why I'm double thinking.
You should get some sleep. Yeah.
Sleeping is not an option, but I'm thinking about exhausting myself so much. But let's see.
I think we can do it tomorrow. Fast paced.
Fast
speed.
paced not going to happen, I know. When you say fast paced means then you are not going to understand. So yeah, tomorrow's topic I have already decided. Uh, but let's see. How many of you have not done the domino and Tromino tiling? Hmm?
The tabulation piece was killing. I mean, getting that tabulation piece
Tabulation?
probably, yeah, that was like getting too
Okay.
much.
What
Yeah,
I will do is I will upload this video so that you can go through it tomorrow morning, maybe today itself, and then we will continue from there. And you at least solve the Fibonacci and Tribonacci, right?
yeah.
Yeah.
Because this topic is important, so it's better that we break it down. Okay, so part 2 will come next time. Okay, so last day we had solved the Fibonacci and the Tribonacci was given as your homework. So today we were about to do the domino and Tromino tiling. Right. We will try to do this. And I hope you have already read the problem statement, but let me open that problem again and try to explain you what it says. $790 domino and Tromino tiling. Okay, so this one I had already coded. But anyway, uh, let's try to understand. I hope you have already solved using the DP approach, right? That was your homework. And I have already shared you a video explaining how to solve this by DP. So if you have not done that, you can look at it again. But it is a standard problem. This domino and Tromino tiling is a standard problem which can come directly in the interview. It is one of the pattern of matrix exponentiation, one of the well-known pattern. Okay, the tiling problem. So always keep that in mind. The recurrence relation type problems, including the tiling problem, can be one of the matrix exponentiation problem. Okay, all the tiling problems are not matrix exponentiation. I'm saying if you can derive the relationship. So in this class, we will try to understand how to derive the relationship, even though it is not directly visible, and how to write multiple equation state vector. We have till now seen only one equation state vector conversion and how to solve that. But in this case, I will be using multiple type of functions, f of n, g of n, like that. And then we will see how to find the how to convert to the state vector and how to calculate the magic matrix from there. Because once you can do for two equations, then you can do for n number of equations. Then you will not have any problem, right? Then your problem will only be to find if the equation exists. Like, do I actually represent this problem's solution in the form of a linear recurrence relation? Then there will be only one problem, because you can solve whether you have one recurrence relation, two recurrence relation, or k number of relations. You can easily solve it. Okay. right? So please go through this problem again. Let me go through it again. You have already gone through is what I'm expecting. So you have two types of tiles, a 2x1 domino shape. So you see that the domino shape can be in the horizontal version, or it can also be tilted 90 degrees and it can be made as vertical. So for vertical, I will write V, and for the horizontal, I will write H, but it is the same thing. It is the same thing with a different orientation. So horizontal orientation versus vertical orientation. Then you have Tromino. For Tromino, I will be writing T. So it is kind of an L shape, or you can have something like this. I will use only these two shapes because I will be filling the tiles from left to right. If you are filling from left to right and you don't want the gaps to happen in the middle somewhere, then you will only be using these two shapes. Because otherwise, let's assume that you have filled these things, and if you happen to make something like this here, then there will be a gap here, right? So I don't want any gaps in the middle because this is about full tiling problem. Okay, so when I move from left to right, then I will be using only these two Trominos. I will not be able to use other orientations. Otherwise, it will leave gap in the middle, and there is no way you can fill one cell gap. And I can fill horizontals like this, or I can use the vertical orientations. So vertical like this. So if I happen to use horizontal, let's say I have put here horizontal, then I will be forced to put another horizontal in the bottom part as well. You cannot just put one horizontal and leave it as it is. Because if you leave it here, then even a Tromino will not be able to cover the two spaces because Tromino needs one space on the top as well. Whereas if the space was somewhat like here, it was already occupied by something, then a Tromino can fill it up. Okay, I think it is up to your imagination, but I'll try to give you some examples too. So, so the first thing is to find out what all orientations I'm going to use. So for Domino, I will be using these two orientations, and for the Tromino, I will be using only these two orientations. I hope it is clear. Okay. Okay. Even though it says about you can rotate it in any shape, and there are many more shapes in the Tromino that you can make, but I will be using only these four shapes in combination. Given an integer n, return the number of ways to tile a 2n board. So a 2 cross n board is the number of rows are 2 and the number of columns are n. Okay, 0 to n minus 1 or something. You can take n number of columns and 2 rows. And I have to start filling it up. You can fill right to left. You can fill left to right. But I will be doing left to right. Okay. So that's my assumption. And it is also saying that you can have a lot of number of ways, and that's how you have to take modulo 10 to the power 9 plus 7. As soon as you see this, you have to use modulo arithmetic concept. You know already how to use that, right? So if you are going to use binary exponentiation or matrix exponentiation, then you cannot just leave it to, the simple code that we had written in the past. On top of that, you have to do mod multiplication. So modulo multiply matrix. Last time we had done only matrix multiply or multiply matrix, right? So on top of that, if you multiply and add, like let's say x times y plus a times b, something like this we were doing, then we have to take mod of m value here. And then we know what to do. The m will be pushed in both of them. So here you have to write mod m, here you have to write mod m, whole mod m. These all things you know already. Okay. In a tiling, every square must be covered by a tile. Two tilings are different if and only if there are two 4 directionally adjacent cells on the board such that exactly one of the tilings has both the squares occupied by a tile. I hope it is clear, right? Okay, in a tiling, every square must be covered by a tile. So if you say that my tiling is done, then there should be no space left. Everything must be consumed. All the cells must have been covered. You cannot have even a single cell void space. Two tilings are different if and only if there are two 4 directionally adjacent cells on the board such that exactly one of the tiling has both the squares occupied by a tile. So maybe we will look at it with some configuration example. So how two tilings are different, it's trying to say by definition, but I think it is easier to understand by seeing the example set. So you see here that initially, I mean, we are trying to tile 2x3 board. So if you tile a 2x3 board, then it had started with vertical tiling. Okay, so there is one way to tile in the vertical order. And if it is tiled in the vertical order, we have put horizontal tiles, and that will be counted as exactly one way to tile it. How can the second way be different? If it looks different, then it is different, isn't it? It cannot, I mean, the final figure should not be superimposed on top of each other with all the boundaries matching. It cannot happen. If you try to superimpose this second one on top of this, then can we have all these boundaries matching? It's not matching, right? It's not matching. The boundaries here are different. These are the boundaries here, and these are the boundaries. So if you superimpose, they will not exactly match with all the lines. So that's how it is a different configuration. And it will be counted as one more configuration, right? So I think it is clear. If it is not clear, you let me know right now. So it is saying that with 2x3 size, I can do it in 5 ways. So here n is saying about the number of columns, and the rows are fixed to 2. So how many ways we will get is 5 ways. Is there any confusion in this diagram? That is what that line is saying on the top, but it is difficult to understand just by reading it. So I think with they have given the figure, so it's good. Okay. So okay, what can be a simpler approach to solve is you can try by recursion. Like let's try to mark the boundaries, maybe create a matrix in itself. The simplest solution would be to have a 2x n board and then try to mark it. But let's see if I can even create a 2x n board. So I think n value being 1000, 2x n will be around 2000. So 2 times 10 to the power 3. And if you take integer type, then that is going to be 4 bytes. So how much it is? 8 times of 10 to the power of 3. Right. So how much it is? 8 KB. So not even MB. So I think space complexity should not create any kind of problem. So you can start your simple solution by taking a 2x n size board and try to solve it uh, a little faster. That if you are trying to go with the recursion approach, then you can go with the space complexity and then start and see, do I even need the space? Maybe you do not need the space because you just need to track two, you can say K and K plus 1. These two columns needs to be only checked. That's it. You don't need to check anything else. Because if you are at some K plus 1th column, then the vacant spaces can only be present at K plus 1. Everything to the right will be vacant for sure. But in Kth, you can find 1 or 2 vacant cells. But before that, everything must have been filled already. Otherwise, you will not proceed. So can that logic actually save on some space? You can think about that. So I have already explained the solution using, I think, dynamic programming. So please watch that if you haven't done this yet. So let's try to think in terms of recurrence relation for this. Maybe it is not visible directly. Definitely it is not visible. So I'm telling you that it is one of the pattern. The tiling problem is a pattern of matrix exponentiation. So you have to remember, keep this in the back of your mind. So if I force that, okay, tell me about a recurrence relation. What can be a recurrence relation? Like it seems like completely blank. What is a recurrence relation even? Recurrence relation means that my current state answer depends on my past states. I don't care 1 state, 2 state, 3 state, but can I say that if I am at the kth column, then my past configuration will affect the number of ways here? I think yes, because let's say you had filled all these cells, okay? Then will the way in, yeah, I mean how you have actually filled this up affect the total count moving forward? Yes, it will affect, because if you have filled in this way, then how you had filled in this way. You have to keep that in mind. Was it horizontal? I mean, was it vertical, 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 vertical? If you had done in this way, then this is one configuration, and on top of this, we are trying to build. Or have you done this with some kind of Tromino? That means, let's say that you had filled one Tromino here and you have filled one Tromino here. So are you proceeding building on the Tromino, or how you are doing? So maybe it is not very much clear here, but let me show you with some simpler examples. Let us see a function. So should I proceed to this black background? It will be easier. Let's say that I define a function f of n, which says about the total number of ways to fully tile 2n size board. Okay, I can define a function in this way. And there are actually two types of tiling. One is that horizontal vertical bar. That is one type. Another type is the Tromino. Because why they are considered different? Because only having the domino, you cannot have something like this, that you have a vacant cell here. This case will not happen. Either you have both the cells empty, or you have both the cells full. You cannot have one cell empty. This one cell empty case is only possible with the Tromino. It is not possible with the domino. Like, think about it. I don't care how many cells you have. Try to only take the domino, whether it is vertical one or it is horizontal one, and try to give me a case where you say that this is empty and this is full, and you are filling from left to right, and all the cells on the left side is full. I mean, you cannot fill this as full and say that it was empty, right? So those kind of cases are not allowed. Okay, so if you are at this ith column, you cannot fill anything on I plus 1. But can you have such kind of cases? I don't care how many spaces you take on the left side, but it will not be possible to get to this case. So what I'm trying to say is, with the domino, there will be exactly one case, which is, I don't care whether you put a horizontal bar or vertical bar, it will be like the entire column will be empty. Entire column will be empty, isn't it? But this will give me two configurations. Like, let's say I say that this was full, 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 and everything to the left was full, and this is empty cell. Then in this case, at this empty cell, I can apply horizontal bar and go to I plus 2 directly. Or what I could have done is, I will apply vertical bar and I will go to I plus 1. This means what? This means two states are defining the answer for one state. F of n is related to f of n minus 1, f of n minus 2. Because if I say that ith column is the one where I will be ending my fill up. Let's say ith cell is the one where I will be ending my fill up. Ending my fill up means, after doing this ith operation or whatever operation, I will be full till the ith column. If that is how I'm defining it, then in this case, don't you think that I can still stand at I and I can fill two horizontal cell and say that it is one configuration? From I minus 2, I can go to I in this one way. Is it true or not? Well, one way, right? If I have to say that I have to fill it only with the horizontal cell, then it will be one way. Another way would be to put by vertical cell, but by only one vertical cell, you cannot cover two columns. So in that case, you would have been filling I minus 1, and there I will say that I can use one vertical, you can say a bar, and I will get one another way. Now let me ask you a question with the horizontal cell. Let's say that there are k ways to get this, k ways to generate this, I mean to tile this, k ways to tile whatever is the configuration here, 3 by 3 or whatever, right? I mean, not 3 by 3, 2 by 3. So 2 by 3 k ways to tile it. Then if I say that I can do this in one way, then how many ways do I have to tile this? If there is only one way to extend from I minus 2 to I, there is only one way. If I assume that there is only one way to extend it, then how many ways can I say that is there to tile 2 by 5?
K.
K.
Yeah,
K
k
only.
ways, k ways, right? So can I not generate a recurrence relation where I say that f of I is equals to f of I minus 2? Because this is considered as one, I mean the same configuration getting extended, because I'm not able to do any more configuration than one. So if only one configuration is done, then the number of ways in which you can fill it up, multiplied by the k number of ways that you could have filled till I minus 2. So I said that I will be doing it in one way. So f of I will be f of I minus 2. Okay. So I hope that is clear. Now, so this case is clear, right? There will be other cases. So this case is clear. With the domino, there are two cases. This is the horizontal case. Let me come to the vertical case. So let's say you have F here, and then you have empty cells. Now I said that this is full and this is, so there are k ways to fill it up. And this is I minus what? I minus 2, or let's say it is I minus 1, and this is my ith cell. Now in this case, if I have to fill till the ith cell, can I use horizontal bar? I cannot use horizontal bar, because horizontal bar will cover two columns. It will not cover one column. So in this case, if I have to fill it up, then I have to do it in one way of vertical bar filling. So how many ways will there be to fill this up? K ways exactly. So what I can write, I can also write that f of I also depends on f of I minus 1. Now, since these two are in, you can choose them independently. You are free to apply whether horizontal or vertical. So this will be additive, and you can write it as an addition figure. Because either you go with this way or that way. Whatever way you go, you get x ways here, y ways there at the end. Then you have to add them up, right? You cannot multiply because these are independent. If they would be dependent, then you will multiply. Like if I was building this answer on top of the k ways, because I'm extending it, so I will be multiplying. But if it is going in a different direction, this is going in a different direction, then you cannot multiply, you have to add it. It is like in the probability also you have that thing, right? In the independent probability, you have to add the things. And multiplicative probability only comes when one event is related to the other. Like what is the chance that I will be, I mean, I came to office late, and I was in traffic. Because of that, I went to office late. So there are two related events. I went to office late. That is a sure event. And another event is I was like late because of the traffic. So in that case, you have to use multiplication. Or maybe what is the chance that I tossed the coin 3 times and I get all the times head. Like the Rohit Sharma example, which I had given, right? Always he kept telling tail, and every time it kept coming head. So what is the chance of that happening? So that is a multiplicative type of probability. Yes.
I still don't understand how we came to this additive thing here.
Okay.
Can you explain it
Okay.
again?
So
Yeah.
additive thing is like you see that when do you multiply? If you say that you have two event, you have an event of eating outside. Let's say on 25th of December, you will eat outside and you get food poisoning, something like that. Then what is the chance of you getting, I mean, eating outside is, let's say, 60% chance. And what is the chance of you getting food poisoning? Let's say 0.05% chance. Then if I ask you that what is the chance of you getting food poisoning due to eating outside, you will multiply this, because these two events come one after another. Okay. Now,
Hmm.
if you ask me that why there were k ways here. Okay, why did I write that there are k ways to fill up to ith column? Because up to ith column, I had k ways to fill up. And on top of that, using horizontal bars, I can only fill this 2 by 2 board only in one way. Okay. Let's say that I had more ways to fill up. Let's say that I had 3 ways to fill up. Then there will be 3k ways. Why? Because the previous things, how you have filled it up, in how many ways you can fill domino, tromino, I don't care. In how many ways you filled up, on top of, for each of those ways, you are doing this. It is like a for loop where I will say that, okay, these are the 3 ways. 3 ways are there to fill this 2 by 2 board. Then if I use 2 tromino, something like this, then for this you have 3 ways. Or if I use horizontal and then you use vertical, then for them as well, you will have 3 ways. So many other configurations I can generate. I for k number of configuration, for each of them, you will have 3 ways. And that is why you will be multiplying in this case. So if events are related, then you multiply. But what happens if I say that, oh, this and this configurations are same count? Okay, I totally understand, same count. But if you put vertical here and if you put horizontal, then they are two different configurations now. They're two different subproblems now. And now from there, you are extending them like a branch of a tree. So till now, it is like you are following a tree structure in your structuring, in your hierarchy. And then you came across this 2 by 3 here, from where whether you will put vertical or whether you will use horizontal. So this will give rise to two different sides in the branching. And you know how many ways will there be? Whatever is the return value here, A ways, B ways, it will be A plus B ways here. Right?
Okay. Right. Okay.
Yeah. So
So
it is like
f of I indicates the number of
the number of ways I can
ways.
fill till the ith index.
Okay, got it.
Okay.
Okay.
Yeah. So I mean, you can also think in that way that I will be giving here 2 by 4 and I will write certain number of ways so that they both become consistent now. The ith column becomes consistent, right? Okay, in that way you can think. But otherwise, if you are confusing that I have taken 4 columns here, I have taken 5 columns here. No, I wanted that. This is ith column. This is I minus 1th column. This one. So just to make sure that we are doing consistent diagram. So for that reason, you will understand now, right? Okay.
Got it. Thank
So
you.
domino relationship is done. Now, so if the question was with domino, this is the recurrence relation and you can solve by exponentiation right away. No problem. So I will come to Tromino, but let's think that this problem was only about domino. And this, if this problem was with domino, you know the recurrence relation, you can find your, you can say state vectors. What will be the state vector here? Easy, right? S of n or something, you can write S of n minus 1 as f of n minus 2 or f of n minus 1, something like this. You can write because RHS, all the unique things you will write. And then you know Sn or Sn minus 1, whatever you write. And then you reach to Sn by multiplying with m. So you know Sn is also going to be something like f of n minus 1, f of n. And then because one step switch we are doing, so you know the magic matrix, what will be the dimension? And what will be the dimension? It is 1 by
2 cross 2 dimension
So in
matrix.
this case, I'm taking a column vector. Last time I had taken row vector. So if you are comfortable with row vector, please take row vector. Comfortable with column vector, take column vector. And this is 1 by 2. So you know this column and this, this column, right? It is going to be 2 by 2, isn't it? P cross Q, Q cross R, P cross R. P cross R. Yeah, P cross R. So this R comes from here and this Q comes from this column. So 2 by 2 matrix, right? So I can write A, B, C, D as the magic matrix. And now you have to find the base cases. How will you calculate the base case? For the first column, in how many ways can you fill? Exactly one way. F of 0 is going to be 1 because with this configuration, two rows will always be 2. So I'm not counting it in any kind of variable. Only the columns are going to change. So this I will count as, you can say f of 1. I mean, I will not say 0 because I am having one column, right? So you can have your definition like this, one column. So there is one way. If I have two columns, then in how many ways can you do? You can do in two ways, which is horizontal barring, or you can do two vertical bars. So in two ways. So f of 1, f of 2, I know. F of 3, you know it is 5. I think in the answer set it is given 5. So you can use these three, fill up these values, and then find out the magic matrix and calculate it. Then find the exponentiation for the nth step and get this done. Okay, I'm not doing all the steps because I hope that you have practiced the last class. You have heard the last class, right? So this is the recurrence relation. And I think now you should understand that even whatever is the problem, you can, it will require some practice, yes. But uh, if you sit down and think, not in the interview, but maybe when you are solving some question, then you might come across these things, that there is a recurrence relation. Maybe when you read somebody's solution, then you might understand that, oh, this guy has done using maths. And then immediately it will hit your mind that, okay, it is exponentiation. So you will trace back and come back to solving the problem yourself because you know all the things. So I will understand that you could not do it by exponentiation in the first go, second attempt, third attempt, fourth attempt, but at least you know how to do it. So 3, 4 times when you see other solution, then after that it will start clicking in your mind too. But you do not expect this to happen magically. I do not expect this to happen magically as well. It will take time. But you have to keep it at the back of your mind. And tiling problem, definitely you need to remember that because this comes in interview. So we know this, I mean, this will come in the bad days. This will not come in the good day. If you have good interview, your everything is running fine, then these questions do not come, right? So we are preparing for bad weather. We are not preparing for good weather here. So I think so we are clear with the domino. So let's add one X factor, which is the Tromino. So let's go to the next page. I think so. Okay, Tromino. So I have given you the definition for f of n, right? Ways to fully tile to n. Let me write it again. Ways to fully tile to n board or to n tiles. And I will define another function g of n. Why I'm defining another function? Because I will be calculating for different type of, blocks. So if you have 3 type of blocks, you must write 3 types of function. You have 2 types of block, domino and Tromino. So we will be using 2 functions for that because will, they work in a different way simply. So the number of ways that you get for I, which is dependent on I minus 1, will be different for domino and the count will be different for Tromino. If the count would be same, then I do not require extra function, but it will not be same because the shapes are different. And that's why you need extra function. So let's at this time assume that if you have not understood, let's assume that since the shape is different, the configuration count will be different in the same space, in the same tile size. So I will be defining it with an extra function called g of n. And g of n will be, let me write, ways to tile 2n, where the last column, which is the nth column here, it will be the ith column. When I say g of I means ith column, g of n means the nth column, where the last column has exactly one empty cell. One empty cell. So what configuration are we talking about? This configuration where this cell is empty, or I can talk about this configuration where this cell is empty. I have to make the empty cell always go on the right side. It cannot go on the left side, otherwise I cannot fill up the type. Okay. Okay, so in this case, G of n will be treating both of them as one count only. So when I say that this is full, 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 and here you have empty, and you have put a Tromino here, followed by a vertical domino, or you could be full here, full, 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 and empty. You could have followed another Tromino with a domino. These two configurations are counted as only one count in G of n. Because what G of n says is, in how many ways can I fill the nth, you can say, oh, okay, not in how many ways can I generate one empty cell in the nth column? One empty cell, but it never said about where I will generate it, whether on top, bottom, I don't care. I'm just defining this function based on the count. In how many ways can I get this? So can I say that it can be a function of f of n minus 2? You think about it. Let's say that I just use domino on the left side, domino, whatever I use. There are k ways to do this. Okay. And this is the nth column, and this is the n minus 2th column. Up to n minus 2, everything was full. Let's say everything was full up to n minus 2. Then in how many ways can you get this one empty cell in the nth column? How to define that?
One.
Okay. So how to define that? So you see that if this was f of n minus 2, let's say f of n minus 2 is equals to k. There are k ways to tile this entirely using the domino and Tromino combination, whatever it is. So ways to fully tile to n. F of n is the ways to fully tile to n. It never said that fully tile using only domino or only Tromino. It just says that everything is completely done till n minus 2. If you are completely done, then after this, there are two ways to get this nth column one empty cell. There are two ways. So if there are two ways, then can I not write that g of n equals 2 times of f of n minus 2? Can I write this? G of n here says that the count of total number of ways to get one empty cell in the nth column, that will be equals to 2 times of f of n minus 2, because I can have two different configuration for the Tromino to get one empty cell in the nth column, and therefore I have to multiply 2 times of in how many ways I can fully tile at till n minus 2. Because when I sweep, you remember the line sweep? When you sweep from left to right, left to the line, everything is solved. You do not solve line sweep problem going back again, right? When you say I'm sweeping through the region 1D, 2D, your left side must be done. You cannot look back. Okay, so in the same way, like you can think it like an idea of the line sweep going from left to right, sweeping across and on the left of the line, everything is solved. On the right of the line, I need to solve. And the line actually shows my current area of interest. So my line is here and I have swept over this region. Okay, think in that way. Okay. But is this the only way in which I can generate the nth column vacant space? One vacant space, think about it. Yes. Yes, Soumya.
So Surya, you had said that earlier for G of n ways, if you have to have one empty cell here in the last row,
This one you are
then
asking one count.
yes, one
Okay,
count.
so
You had
this
said this is one count,
so this
but
one
when we
count is
are
about
doing
this one count is about, okay, I'll come back to it. So let's ignore that point, because when I write the full recurrence relation, then you might get confused why I'm multiplying by one or something. So let's keep it aside for the time being. Okay,
Okay,
and
so
let's
the two that you have here in this one, so that is because of
this is fully tiled.
yes,
Okay.
yeah.
After
So
this,
this
you put
two
this cell
this two is
or
because we have these two configurations. configurations, right?
These two, yeah. So these two configuration. So either you
Okay,
get
got it.
this kind of configuration, or on the fully tiling, you get this inverted L.
Okay, got it.
Yeah.
Okay, so
So
we
now
have
you are
to,
branching.
so
Hmm.
this we'll ignore for now, the one
Yeah.
count where you
Yeah.
said, okay,
Yeah.
got
Okay.
it. Okay. Hmm.
So let's ignore that one count. I'll come back to it. But let's say that this is one thing that I can do. But can there be another way to get nth column having one empty cell? You are free to extend this fully tiled, not fully tiled thing. Can you think? I will give you a hint that you can do that without using a Tromino.
Just Domino. Just use Domino.
Yeah, so let's say that it is completely full here. Let's say fully tiled. And after this, you had Tromino here. Okay. And this is your n minus 1th column. And this is your nth column. So my question is, can I generate one empty cell in the nth column? I can put a horizontal domino and get one empty cell here. Or in the other way around, I could have taken a Tromino like this, and I could have placed horizontal bar and could have got a empty cell on the top. So depending on whether the previous one was a Tromino at ending at n-1, I can have two ways again, isn't it? Two ways to do that. But what is g of n-1? If I count g of n-1, what is that? G of n-1 says that the total number of ways in which I can have the n-1th column having an empty cell. That is the definition, right? Ways to tile to n where the last column, which is the nth column here, and here n-1th column, has exactly one empty cell. Okay. So it is not two count. It is called g of n-1. It is not called 2 times g of n-1. That's why I had written one count here, because g of n-1 already says in how many ways can you get the up to n-1. I mean, in the n-1th column, you should have one empty cell and rest all on the left side must be full. In how many ways can you get it? It is g of n-1 ways. Is this definition clear?
The empty cell can be on the top or bottom,
Yeah.
right?
Yeah.
Okay.
So there
So
are two
one.
configurations here. And that's why I said that we will not be multiplying by 2, because g of n-1's definition already covers the total number of ways in which you can actually get it. And that already includes 2 times f of n-1, right? Yes, Amar.
Yeah, so over here, Surya, where we say g of n is equal to 2 into f of n minus 2, right? So
Hmm.
over here, yeah, I understood that there are two ways where we can get empty cell. So this makes sense to me, but this g of n minus, why we are saying g of n minus 1 when we like, it looks like the function should be f of n minus 3, no?
No. So in this case, g of n is not associated with using tiling. So that is one set of confusion generally, that f of n is about domino and g of n is about Tromino. So it is not like that. F of n is about fully tiling up to nth column. G of n is about tiling fully till n-1th column, and at the nth column you should have one cell empty. That is what it means. Are you clear? So when I say f of n, then this means I should be able to tile this fully up to the nth column.
Yeah. So
And when
when
I
you say
say,
g of n minus 1, what does this mean?
so g of n-1 means that when I'm tiling, then I should be able to, I mean, if I give you the definition of g of n, then I will say that when I'm tiling g of n, when I'm tiling, then everything up to n-1 should be fully tiled, and only in the last column you should have one empty and one full.
Hmm.
Either the top one is empty or the bottom one is empty. You should have one empty and one full.
Got it. And if we say G of n minus 1, that means
Yeah,
G of n minus 1 should have one empty cell.
yeah, yeah. G of n minus 1. When I say G of n minus 1, then you just replace it with n minus 1. So up to n minus 2, everything should be full. And n minus 1 should have one empty cell, whether it can be on top or bottom.
Okay.
We have till now not fully derived this f of n. F of n is not fully derived. I will come back to it to derive it even further, but I'm just doing it in parts. Okay. So is this clear? Yeah.
I have a question related to this.
Yeah.
So, for a G of n minus 1 in this diagram here, right? So, we don't have any empty space, right? At G of n minus 1 here.
No, my bad. I am trying to explain G of n here. So you
Okay.
either name this n minus 2, n minus 1, or it is G of n. G of n is in how many ways can you get the nth column having one empty cell? And G of n minus
Okay.
1, how many ways can you get n minus 1th column having one empty cell? So if you see
Okay.
G of
So,
n definition, then you do like this, or you do something like this. Then you have it on top or you have it on the bottom,
for
right?
G n minus 1, however, you stop here. After this, you don't put anything else. No.
No, no, no. You're
Okay.
okay. Let me explain it. So
Okay.
it
Yeah.
is just the naming change, n minus 1 column or n column. So let's understand G of n. G of n is in the last column, you should have one empty cell. So either the top is empty and the bottom is full, or the top is full and the bottom is empty. That
Hmm.
can be the configuration. So in this
Hmm.
case, if I say I have to get to this configuration, then I have to have this portion completely full and this will be
Hmm.
empty. Or
Hmm.
I can have this completely full and this part will be empty. So this is your G of n.
Hmm.
In how many
Hmm.
ways can you get to this configuration is G of n?
Hmm.
Any of these two configurations, right?
Hmm.
So in how many ways can we get it depends on whether the previous one was a domino or a tromino, because maybe I said that this is completely full and on top of this you created a tromino and this created the nth column having one empty cell. So in this case,
Hmm.
you know exactly the definition of f of n says that up to nth column, everything, the entire tile is full. 2 by n tile is full, right? So can't we
Hmm.
say that this is f of n minus 2? Because up to n minus 2, everything is full. And on top of that only, we used a tromino and got to g of n, isn't it?
Hmm. Hmm.
Okay. Another way to say this is, I have till n minus 2, everything is full. And I will use an inverted tromino, something like this. So this
Hmm.
one is empty. Okay, so this is
Hmm.
also coming under g of n. So g of
Hmm.
n can be said to be equals to 2 times of f of n minus 2.
Hmm.
Yeah, so that's what we are trying to understand. So this is by using the tromino on top of f of n minus 2. But I was
Hmm.
giving another configuration to reach this configuration as well, which was about if your previous configuration was something like this, where this was n minus 2, then what will you call this? There was one empty cell here. Will it be called f of n minus 2 or g of n minus 2? What will you call this? Because you can have two ways to do this, right? I mean, something like this. N minus 2th column, n minus 2th column. What will you call this configuration? F of n minus 2 or g of n minus 2?
G of n minus
G
2.
of
G
n
of
minus
n minus g of n minus 2, right? So
Yeah.
Hmm.
if I say that the nth column, I have to generate g of n, then this means one cell should be empty. If I put a tromino here, then it is completely filling it up. It will not create g
Hmm.
of n. It will create f of n, right? So in
Hmm.
order to get g of n here, I have to put horizontal bar. And in order to get to g of n, I will put a horizontal bar here. Then I will get to g
Hmm.
of n, right?
Hmm.
So
yes.
now can g of n be related to g of n minus 2? Yes. G of n equals G of n minus 2, not 2 times of G of n minus 2. You should remember that, because G of n minus 2 is already counting the total number of ways in which you will have one empty cell in the n minus 2th column. And this already, it has already accounted for these two configuration. That is why we will not multiply by 2. Okay, I hope it is clear now, right?
Okay, yeah.
So these are the two ways. So this will also get added G of n minus 2. I think it should be n minus 1. I think so. Nobody corrected me. This should be n minus 1. From there, if you put a horizontal
Yeah.
bar, going one column to the right, isn't it? So this is
Right.
going to be n minus 1, n minus 1. So this is the
Yeah.
recurrence relation with G of n.
Okay. I
We
get
have
it now. Thank you.
we have fully derived G of n, but let's go back and see if we have fully derived the f of n. Where is that? The f of n was f of n minus 2, f of n minus 1. But can we fully tile up to nth column by using Tromino? Because we never use Tromino, right? So you see that we can do that. Actually, if we have this kind of configuration and this is your nth column, then I can use a Tromino to fully tile up to n. And I can do it in the inverted way as well. I can use Tromino and tile it. So in this case, f of n is related to, this is your n minus 1. What it is related to? G of n minus 1. G of n minus 1 is the total number of ways in which you can form these configurations, these two configuration endpoints. Again, you will not be multiplying by 2 because G of n minus 1 already counted these two things. So f of n is equals to G of n minus 1. And so you will also be adding G of n minus 1 there. Okay. So we have accounted for all the cases now to get to the nth column having full tiling. Right, Rajesh? Rajesh, you are not turning on your
Yeah.
video.
Surya,
Yeah,
if it
Surya, I
would
get
be,
it.
if it
Yeah.
was a 2x2 board,
Hmm.
then you won't be able to fully tile it with the Trominos, right?
No. Then with the Tromino, you cannot do that because you will not be able to fill the one empty cell that you get.
Yeah,
Because if it is a 2x2 board, then Tromino will take this, but one cell cannot be filled, isn't it?
right.
So in up to 2x2, we cannot use Tromino. Starting from 2x3 only, we can think about using Tromino.
Okay. Then we
Because
can fully tile just using the Trominos.
because at the end, those ways will be counted where the tile is completely full without having even a single void. You cannot have any void space in the middle. Okay. So I hope you have understood these two things. F of n is this. So let me write it again somewhere. Where should I write? Let me write it here. So what is the recurrence relation for f of n? F of n minus 1 plus f of n minus 2. Yes, Amar. Plus g of n minus. What is this?
No, Surya, I'm good.
Okay, g of n minus 1. N minus 1, n minus 2, g of n minus 1. Okay. This is first recurrence relation, and g of n is equals to, what is that? 2 times f of n minus 2 plus g of n minus 1. So 2 times f of n minus 2 plus g of n minus 1. Two recurrence relation are done. So this is the hardest part, to derive the recurrence relation, because you may miss on some cases and then the recurrence relation will go wrong and then everything will collapse. Okay, so recurrence relation we have found correctly. After this, can you tell me what will be the state vector? What will be the state vector? S of n minus 1 is equals to what? Now S of n should contain both the equations, RHS, unique RHS values of both the equation. So this is the region I'm interested in. So I told you the rule. If you have constant multiplier, you leave that out. If you have constant addition, you will add 1 for it. So what will be the column vector for this? I'll make it later. You can write f of n minus 1, f of n minus 2, g of n minus 1, and then f of n minus 2 is again present. So this will be cancelled out. It is like 3 times f of n minus 1. So 1 time writing is fine. And then g of n minus 1 you have already written. So this will be the state vector. This includes all the unique values, isn't it? I don't care 2 times included, 3 times included. It should be all the unique values. Are we done? If you are done, please let me know. Or if you have any question, then please share the question. Vidhi, I think you are feeling sleepy. So I should ask question to you, isn't it?
Yes, sir. So here, in this case, for f of n minus 2, you are thinking, you suggested that there will be a plus 3. So are we planning to put f of n minus 1 value in place of f of n minus 2?
Yeah, so we will be doing for the base case, like find for f of 1, f of 2, f of 3. Because how many states do we need? I think we need only 2 state transitions. So f of 1, f of 2 will go to s of n minus 1 state, and f23 will go to the resultant state, and then I can find the magic matrix. I hope this is clear. If this is clear, then I can write s of n equals just transition one extra state. It will be n. This will be f of n minus 1. Add 1 value to all the states. Okay, so this is your s of n. And then you should multiply with the magic matrix and get to s of n. Now you find the dimension of the matrix. It is 3 cross 1, right? And this is also 3 cross 1. So you know
So 3.
P times Q. What is this? Q times R. And this is P times R.
So can we write just m will be 1 1 1 1 0 0 and 0 to 1.
What 1 1 1? What you are saying? I
I'm
didn't get
saying
it. What will be the magic matrix? Size,
3
dimension.
cross 3.
3 cross 3.
Yeah. So it is always a square matrix that you are going to get, isn't it? PQ, QR. What is this?
PR.
PR. So how much is the dimension coming?
Q
Why
cross
it is
3
coming?
plus 3.
So this is Q. Why it is coming 1?
No, 3 cross 3 will come.
Oh,
Last one will be R cross P or P cross R?
P cross
oh,
R.
yeah.
M
Shouldn't
we
it
are
be
putting
1
in the
cross
first bracket.
1 because
It will
Q
be
I'm messing up somewhere.
No,
Okay,
yeah.
you tell me.
Surya. See,
Yeah,
SN
it
is
will be 3 cross 3 only. It
1.
cannot be anything else. Yeah.
So
Let's see.
M will come here in the
A,
beginning.
B, C, D,
Hmm.
E, F, G, H, I. Okay. Now you have this. Let's say, what is f of 1? When you have one column, I think it will be 1. There will
One.
be only one vertical way to fill it up. F of 2 will be how much? 2 is. You can have 2 vertical or one horizontal,
Horizontal.
2 horizontal bars, right? So this will be 2 ways. And f of 3, we know there are 5 ways. There is a diagram for that. So you can also derive it. So I can put here something like, what should I say? This should be the smallest value. So this will be f of 1. This will be f of 2. And this will be g of 1.
One.
I'll come to g of 1's value as well. And this is your matrix. And this is going to be f of 3, f of 2, g of
3.
how much? I
Three.
think this is
This
2.
will be
2,
G of
2.
2.
It's 2 and this is 3. Okay. Now you have to fill up the values. Yes.
So Surya, when we are multiplying here these two matrices, then the number of rows for the second matrix should be the same as the number of columns here, right?
Yeah. So Sandeep will explain this. Explain, Sandeep.
Actually,
You are the one
you
who
have
will.
written the order. Yeah. See, actually, you have written m in the second place. Just write m in the
Yeah.
beginning.
Yeah.
Fn minus and F minus 2 in the second place.
Yeah.
Okay.
Whatever
Okay.
feels feasible to you, you tweak like that so that it comes out to be a square matrix. So in the middle, there will always be a square matrix. Okay.
Okay.
So
We
Got
don't
it.
require this f of 2, f of 1. Means we require the value to solve in the last, but to calculate ABC, we don't require f of 2, f of 1, g of 2. We can compare directly. See, we know that a times f of n minus 1 plus b times f of n minus 2 plus c times g of n minus 1 is equals to f of n.
f of n.
Correct. So if you compare A, B, C, it is clearly visible that f of n is equals to 1 times f of n
Yeah.
minus 1. So A is
Yeah.
1 for sure.
Yeah. Okay. So you know how
And
to
B is
equate
1,
it.
C is 1.
How to
Yeah.
equate it? You have to multiply like this.
So we
Or
don't require f of 2, f of 1, g of 2 to calculate now. Means
I
for
like to write
ABC.
in this way. So I always solve problem using this. This is very confusing for me. This is something which I do. That you do in this way and this format. Simple. It is set. So f of n with a and this with d and this with g and compare. Whatever way you like, you just do it. Because maybe if you change the shape of it, you may have to transpose it. So that you have to think. If you don't transpose again, the magic matrix can get wrong. So there should be a thumb rule that you always follow. Otherwise, it is already a difficult problem and you don't want to mess up like this. Like you messed up in the matrix and that's why everything went wrong, isn't it? The hard part is solved already. So anyway, you can find out the magic matrix now, isn't it? What will be the magic matrix? Can you tell me? All of you guys calculate and let me know. Except for Sandeep, all of you calculate because he will say the answer and then you guys will not solve it. So you can take in this way. And then the right hand side you can say f of n minus 1, g of n. So this is the consistent way that we have done in class 1. So you multiply this with this one, then with this one and compare with f of n minus 1 and g of n. Okay. And please let me know the values. Let's see what values you get. I have already pre-computed it. I think so. So anyone got ABC? I mean, I should ask ADG according to what I'm writing. You tell me what all values have you got? Amar, you are joining the session after the session is done.
Yeah, sorry, I will be joining.
Okay.
So ADG will be 111, I hope.
Okay. ADG is 110. ADG. 11
1.
ADG. I got 0.
Okay.
Okay. I may be wrong as well. I mean, Sandeep will only confirm now, right? Sandeep, what is your answer? I got 110 somehow. Let me check my calculation. Or let me just write it down so that we can just clarify it. Yeah, so Are you doing row side, or how you are doing? What equations have you got?
If you're taking this column matrix.
Row.
I'm using row.
I'm using row.
Okay. Okay, I mean, but the matrix should be same, isn't it?
Just take the transpose now.
Okay. You are getting, I think, magic matrix as 1, 1, 1. And okay, you are saying row wise, I think, and I'm thinking about column wise. So maybe you can follow one thing and
Yeah,
solve.
so take the transpose of that, it will work.
Yeah, I think yeah. If you take 1, 1, 1 is my row. For ABC, it is 1, 1, 1. So that's what I'm saying, that you will get
Yes.
confused with the transpose stuff. So you remember only one pattern how to solve it. Otherwise, you will apply one side, and even
Yeah,
you cannot move
I
it
generally
left, right.
solve this.
Yeah, if you move it left and move it right, then again you will get something wrong. So you also follow which state vector I will write first, and then I will write magic matrix, and this is how I'm going to do. I will keep row vector, or what I'm going to do. Because it is always going to be 1 cross n type of matrix, the first one. If you are taking row vector. So I mean, you got to think about it. And also you cannot take this configuration with this configuration. Otherwise, you cannot multiply it. You have to
No,
transpose
I'm
it.
taking M before this matrix, and then
Yeah,
I'm
yeah.
writing.
Yeah. So that's what you move it here, or you transpose the first one. You take transpose, or you move it on the left side. So I have taken the transpose, and I am keeping it on the left side. So that is my thumb rule of solving.
Okay.
So that I don't have to apply my brain into this configuration setup. The less brain you apply, the faster you solve the question, right?
Okay. So so A is 1, D is 1, and G is 1. Okay.
Okay.
Then B is okay, Fn
How I
minus
have
2.
got 0. Anyway, you guys give me the answer. I will write down your answer as well. I think I have got something like this: 1, 1, 0, 1, 0, 2, 1, 0, 1. Have you got the transpose of this? Or I need to recalculate. I
F
had
of n
taken
minus
this.
1 is.
I had taken this on the left side, and I have taken the
Okay, you
column.
have taken. Okay, got it, got it. This is correct because you have taken uh, row
Yeah, I
matrix
have
now, no?
taken
So
this
got it.
this
Correct.
matrix on the left side, and then the column vector, and
So f
multiplying
of
that,
n
I
minus 1
got this
is
magic matrix.
f
Yeah.
of minus 2.
Okay. So
I'm stuck on very easy thing. What will be G2 and G3?
okay, let's write the equation, I think, because maybe we are assuming too many things, right? Let's remove this stuff.
Yeah.
If you take row vector, take on the left side. If you take column vector, keep it on the right side. That's the thing. But you only always solve using one technique. You don't apply multiple techniques in multiple problems. So let's keep this on the left side. So if it is on the left side, you have ABC, DEF, GHI. So let's think about how you will compare with this f of n. So you multiply this with this column. So you will get A times f of n minus 1 plus B times f of n minus 2 plus C times G of n minus 1, which is equals to f of n. Okay. Now, if this is equals to f of n, then you compare.
So A is 1, B is 1.
Right. So this equation is given here for f of 1. You just do comparison of these two equation, n minus 1, n minus 2, gn minus 1, everything is given. Coefficient value is 1 in the original equation. So ABC will be 1. So that's how I have got 1, 1, 1 here. Okay. Now, similarly, you repeat and see what all values are you getting, and check, is it the same? Like with multiply with this DEF with this thing. Let's see. D times f of n minus 1 plus E times f of n minus 2 plus f times g of n minus 1 equals f of n minus 1. So do I have any equation? I think it is similar equation. What do you say? F of n minus 1, f
We
of
have
n
to make
minus
E and F 0 only.
So yeah, so
So E and F
these
0.
two you can compare LHS, RHS. N f of n minus 1 is on the right side. On the left side, there is a term of f of n minus 1. If these two equation, I mean two LHS, RHS have to be same, this entire term has to turn to 0. So I don't know about the function values. If I make coefficient 0, then it will always be 0. That's how I make sure that it is 0. So E and F will be 0 here. So that is what is written, 0. And this D will be 1. So that's how it is 1, 0, 0, right? By comparison. LHS, RHS comparison. And then the third equation you check. Again, let's write somewhere. Let's write here. G times F of, this G is different. It is a coefficient G. So G times F of n minus 1 plus H times F of n minus 2. Now, these all things must be done on notebook. It is not a coding thing to do. You have to derive this all things and then fetch this magic matrix hard code in the code and find m to the power of n minus 1, right? That's what we are trying to do. And equate it to G of n. So look at G of n. G of n is 2 times f of n minus 1. Where is that? F of n minus 2. So h will be 2. Okay, so h here is 2. Fine.
And I will be.
It has G of n minus 1. And it has one coefficient. So this is going to have one coefficient. Where is I? It is 1. And so, and this G of n minus 1 term, I think, which one is not present? G of n minus 1 is not present. Because for G of n, n minus 1 was present, right? So you can expect that it is going to be 0. I have to nullify that entire thing. Right? So because we were writing for G of n. So for this, we had G of n minus 1. We didn't have this f of n minus 1. F of n minus 1 or f of n minus 2 was present. Okay. So yeah, with some practice, you will come to know about this. But anyway, these three problems are the main problems in interview: Fibonacci, Tribonacci, and tiling problem. Okay, so we have found the magic matrix. Now, if you want to go to nth state of f, because it is asking about fully tiling on a 2 by n size board, fully tile it. So maybe I will find m to the power of n minus 1 and do n minus 1 straight transitions. So I will be reaching to, I think, f of n and f of n plus 1. So this middle one should give me the answer, f of n. Something like that, right? Everyone will not give me the answer. So you just understand like which cell is giving me the answer, how I have written it. So I will always prefer that you write in increasing order of each variable. That is how I told you, right? So in that way, you will always make sure that the first cell is my answer. And don't try to do over optimization that I will do n minus 2 and second cell will be the answer. I will do n minus 3, third cell will be the answer. So in that way, actually, you will find it difficult to debug as well. Because if there is some small mistake, then you will think this is the mistake. Then you know what happens when the mistake is small, then you take two pieces of code and compare line by line that, oh, did I miss anything or not? And then at the end, you will copy paste this thing entirely that, okay, still it is not running. Let me copy paste the thing that I had written in the past. So you don't want to run on those things. You don't want to waste your time. So stick to a pattern, which is n minus 1, I suppose. Okay. So we have found the magic matrix, and I think you can solve the problem. So can you do some kind of coding, or should I tell you about writing the state vector techniques? Let me tell you some more techniques for that. There are two techniques in which you can make the state vector. I have told you one technique. The second technique I'm not going to tell you, because if I tell you, then you will get confused about. Okay, I will tell you only one time. Okay. So don't remember it.
Sir, can you go
Yeah.
back?
Yeah.
The last you said f of 2, like we should give it in a sorted order. So here we need that answer for like n will be value of f of n minus 1 and g of n. That itself is not sorted. So
Okay, we will sort it, because when we write on the right side, exact same order should also be present on the left side. We cannot have f of 2, f of 1, g of 2, and on the right side 2, 3, 3. That thing will not happen. You have to write f of 1, f of 2, g of 2, and corresponding result will come out, isn't it?
I see. So
Yeah, we should not change only one thing.
so whichever is in the recurrence relation, we
Yeah.
just need to put that in a sorted order on both the
Yeah,
sides.
yeah. You find the state vector, and if you want to go to the next state, you just add +1 to each of them without changing the position. If you change the position, then that is not going to be correct because comparison will fail in that case. So you will not get the correct magic matrix. Then you cannot solve the problem.
So,
right? You cannot change it.
So in this case, f of 2 is first and f of 1 is second. So if we change the ordering on both the side, then is it okay?
It is fine. It is fine.
Yeah, because it is in
It is
relation,
fine.
it is in additional, so we can
Yeah.
do it. But okay.
Yeah. Okay.
Got it. Yeah.
It has to be consistent. Whatever state vector you have taken, it will always be fine, but you have to know which cell will give me the answer. If you keep it sorted and do n-1 transition, then the smallest one, which is the topmost or the leftmost, is going to give you the answer. So that's easiest to actually, debug and see the values. So that's how it is. So I have stopped here. Let me tell you the two techniques in which you can write the state vectors. So I have only given you one technique because I don't like to follow the second technique, but I'll tell you. You don't remember this, okay? Now I'm telling you and then I'm asking you not to remember. So what should be done? If I say that don't remember, then people remember that the most, isn't it? Like when people say that don't talk loudly, then people start talking loudly. I mean, I don't know why. This is a reaction. A minimal dependency state. This is what we have been doing. Minimal dependency state. In this technique, we take only unique RHS variables. Only unique RHS variables. So let me give you a question and you please give me the column vector for that. Example, A of n equals A of n minus 1 plus B of n minus 1. B of n equals 2 times B of n minus 1 plus 5. C of n equals C, uh, C of n minus 1 plus n times A of n minus 1. So please give me the state vector for this. S of n minus 1 or S of n, whatever. If you take the unique RHS values, you will get S of n minus 1. Because all the values are in n minus 1 only. Starting, you will never have a nth a step here because nth step is what will be the result. So current state, if you take the RHS, it is the n minus 1th result that it is showing, n minus 1 and the previous results up to n minus 1. Using this, they are calculating the nth step result. So when I write the state vector using up to n minus 1, then I will write S of n minus 1. I will never write S of n. Okay. So if you are confused, why not S of n? So I gave you the reason. So can you find out the unique values? A of n minus 1 is one value. Can you proceed?
B of n minus 1, C of
Okay.
n minus 1, and
C of there is
maybe
B of n minus 1 done. C of n minus 1. Okay.
then
A of n
then
minus
for
1 done.
that's
Then
also done. I think for accounting for the constant, you have to add a 1 plus 5 is there, right?
we have to add a 1
This
or yeah, we have to add a 1.
yeah, yeah, that's
And
what I meant. Sorry. Yeah.
we have a scalar here
Oh, okay.
because this is n. If it was some constant c, I would ignore that. But this is n. So what should be done? For n, you can include the step number n minus 1 simply. N minus 1 or n, whatever you take. I'm just taking the step number. Because in every step it will increment by one value, something like that. Nth step it is, if the n equals to 5, it will be 5 times a of n minus 1. If n value is 4, it will be 4 times a of n minus 1. So I'm just keeping it as n minus 1. You can also keep it as n. But let's keep it as n minus 1 for s of n minus 1. Okay, and you know what will be s of n? What will be s of n? You add one value to each of this. A of n,
B of
B
n.
of n, C of n, n, and 1 will remain as 1. Because this 1 is only for the constant. Because anyway, I'm just going to multiply it one time. State vector multiplied by m to the power of n minus 1, right? So only one time multiplication will be done. I'm taking 1, always take 1 for plus minus of a constant. That's it. You can also consider minus value if it is minus, but I will always take 1. Let's just take in that too. Okay. So this is the technique that you know. This is the technique that you know, and I follow this technique. But let's see another technique. I think it is clear, right? I have taken a little weird kind of example so that you will go back and start thinking about it. Canonical or block state. So in this case, it says that take largest backward index, take largest backward index and calculate all variables till that index for each type. Okay, let me again come back here. And it means that what is the largest backward step? Like if n minus 1 is the most recent one in all of these RHS, then what is the most backward? The most backward is also n minus 1 in this case somehow, because everything is n minus 1, n minus 1, n minus 1. But let me go back here and try to write this one. Where is it? Where is our recurrence relation, by the way? Somewhere we had written. Okay, so let's write for this thing. In these two recurrence relations, the most recent is n minus 1 and the most backward is n minus 2. So I will say that I have to go, not L, let's say steps. I have to calculate till 2 steps. 2 steps back from the most recent n minus 1 step. So in this case, I will have f of n minus 1 and f of n minus 2 because I know I have to go back 2 steps. Another function is g's function. So I have to calculate g of n minus 1, g of n minus 2, because all the variables need to be calculated to 2 step backward, whether you want it or not. So f of n minus 1, f of n minus 2 covered, g of n minus 1. G of n minus 2 was not present, but that was still added. Because the definition says that for all the variables, you have to go to the maximum backward step. That means if any variable goes to, you find the variable which goes to the largest times backward and take that space and apply it on all the variables. So that's how you will end up taking more variables here. But I don't like this because you will have to do more work, isn't it? You will have to do more work. Why should you do that? So simply take the unique RHS that will always be having less than equals effort. Minimal dependency will have always less than equals effort as compared to this technique, the canonical block, isn't it? Because here you will end up winding up doing more number of steps, more calculations. So that's why I don't like this. Okay, simple reason to reject. Whereas in this example, I think it will be the same because the most recent and the most backward is always n minus 1 here. So you will end up maybe with the same state vector and there will be no change in the state vector, but state vector will be larger generally for canonical. If some goes 3 steps back, 1, 2, 3, some goes 2 steps back, some goes only 1 step, then you have to make all of them go 3 steps back and write nine entries. Whereas in this case, you could have written 3 plus 2 plus 1, 6 entries, isn't it? So that's the optimization. So let's see the code for that problem. What do you say? So that you can go ahead and code it later, because I have already coded it, so that I don't have to code it on the go. It will be too much time taking. Fibonacci itself had taken so much time, right? So first of all, before starting, now this code I have taken in a sense that will suffice the senior engineering interview, because if you are SD, if you are giving for SD1, you can write whatever you want, you make it run, and that's fine. But if you are giving for senior engineer roles, structuring is important. Definitely, you define constructors in a good way, write the code. I generally do not write in this way because it consumes half of my brain in structuring only, right? Whereas I want to just write whatever way, like it should work, isn't it? Or anyway, so see, this n value is 1000. Okay, if it is already saying that you may have overflow, never take integer for these type of cases. Because if you can have overflow, then definitely you should go for 10 to the power 18. That is your long integer. So here you see that I have defined int 64. So why int 64? Because you cannot define int directly here. And it is a good thing that in the code base, in the companies, you will find using int 64, int 128 like that. And int 32 as well. They don't use integer. They also use int 32. So as to make everything, in the same grouping, int 32, 64, 128, int 16 as well. It makes sense. Everything can be comparable. So that's why we have taken not just long. It's easier to read for other language people too. And then the mod value. Okay, it's a constant. You just define constant. Then we can define a structure. Okay, defining structure actually brings everything inside, and you can also have constructor for the structure object definition. So generally, people do not write constructors for structure. They write the constructor definition as a function outside. So that's not a good way to do it. Even something they are doing like node merging, something on the node they will do, creating a node, merging the node, some logic on the node of the structure. You should write it inside the structure, because you can always write the functions related to structure inside the structure, so that all the logic is at the same place and it is the logic of the structure node. So that makes it much more readable, easy to debug as well. You know what you are looking at. If you write five functions here, then it will be difficult to understand for somebody else what is going on actually. So maybe you will also find it difficult to debug. So in this way, that in this case, I have to take a 3 by 3 matrix, obviously. So I have already hard coded it, because before solving any matrix exponentiation, you must have the magic matrix with you. Unless you take that, you cannot solve it. So you should derive the recurrence relation. If you are giving interview, write it in the doc, recurrence relation, then show the magic matrix. Maybe you can write the final value. They will understand. And then you can start the code. So once the magic matrix is correct, then only people will ask you to code. Otherwise, if they do not remember the magic matrix, then also they can ask you to code, but you will not get all the marks cut if the magic matrix is wrong, because that's not a big mistake. I do not consider it like a big mistake, because it should be like, the technique, the way you actually relate a problem to matrix exponentiation have a lot of marks, and finding out the recurrence relation has a lot of marks. And then writing the code using binary exponentiation and modular arithmetic with matrix multiply has a lot of marks. Least number of marks is about the correctness of the magic matrix in the face-to-face round. They don't care about it too much. They care about your way of thinking and the process. Whereas if this question comes in the OA, everything comes down to the magic matrix. Otherwise, then, the invert things happens then. But in OA, you will not get such kind of strict cases where you have to apply matrix exponentiation. Generally, you will not get this in the online assessment. It is not an online assessment question. So, let's see. So you have taken this, the matrix 3 by 3 size, the constructor definition, setting this entire value to 0, presetting to 0. Okay. Okay, I can take a vector and it will always have preset value 0. in C++. But if I take just array subscript, then you have to preset the value. Then let's see these matrix multiply, because it is a utility function, right? So it will take two matrices and it will multiply using modular arithmetic. That's it. It is the same piece of code that we had seen in the past. Last day we had seen this exact code, right? In this code, however, I'm using a dot a, r dot a, because these are you see object of this structure, right? A object and B object. So if I have to access this A, then I have to write object dot A. If it is a pointer type, then I have to give an arrow, isn't it? If it is non-pointer type, then I have to give a dot. Okay, so I have to give a dot. I have already taken the reference, so I have to just give the dot. So with dot, I'm accessing the objects matrix, and I'm just doing matrix multiplication. Exactly. I mean, it is the same code. I hope you don't have any question. The only thing that differs is this thing, mod of this MOD. And by taking long integer, you make sure that you don't have to apply a lot of brain in multiplying this and then again applying the mod. Otherwise, if you take integer, then you may overflow by just doing one-time multiplication as well. So by taking long integer, you make sure that even if 10 to the power 9 is multiplied by 10 to the power 9, it reaches to 10 to the power 18. And still it is within the 64-bit integer. But if there are three multipliers, then remember that you have to take mod after every pair multiplier. You cannot have three multiplications going on with this range of value in a 64-bit integer, because values can go to 10 to the power 9, and 3 times multiplying 10 to the power 27 will definitely overflow. So if you see this kind of, pair writing somewhere, and you think like, okay, mod should be outside, then if I say A times B times C, then you cannot do. Then you have to do A times B whole mod and then multiplied by C whole mod. Like the chain multiplication, chain mod, which I told you, right? If you remember, A times B times C times D mod should be written as A times B mod M times C mod M, okay, times D mod M, something like this. So that after each multiplication, you are making sure that even if it is the largest value here, still it is in the long integer range. But if you multiply 3 times, then you can overflow.
At line number 17, should we also, would it be better to do A dot A modded with
Okay.
mod, and then
Yeah, you can
apply
do
the
that.
chain thing here? Okay.
Yeah, you can do that. But I know it will not overflow, because 10 to the power 9 added with 10 to the power 9 is only going to be 2 times of 10 to the power 9. So it is not a power addition. It is just like coefficient will increase by 1 in the plus. But yes, it's a good
Okay.
practice that you also put a mod here and then you put a mod here. So
Okay.
that you maintain extra safety. You while debugging, you don't want to debug this thing. So while writing, only take care. Okay. So this thing you know already, you can refer back to the past code. This also you know. This is just binary exponentiation, nothing else. So what else have we done here in the tiling? The hardest part is already done. And here, just the base case n0 and 1, you just return 1 value. I think so. It is writing 1 here because there is exactly one way to tile 0. No columns, you don't do anything, and that is one way. Okay, so that's how I had returned 0 here in the past, but it expected 1. So that's how I came to know that, okay, it is also counting that not doing anything as 1 count. If you don't have any space, then you don't want to fill. I mean, it is just the knapsack concept that if your bag is empty, and then in how many ways can you actually fill the bag? Maybe one way. Okay, you can think about it, but yeah, anyway, it can be 0 as well. So here I have written the recurrence relation. For each of the recurrence relation, what is the matrix value? I am writing it. Okay, which recurrence relation I'm comparing it to, I have written. Okay, how it is compared, how I have got these values, but you know how to get it. So you need not write these values. You can also write directly m dot a 3 by 3 or something, whatever spaces equals. You put this and you write a b c comma comma separated, and then you write three values, and you maintain that in each row you write the value rather than writing it in the entire one row. Otherwise, it will not be readable. So this is a good way to write, but this is one way to for people to understand. And then this is the calculation, how I have done the calculation. Okay, that's it. You want integer, so you have to typecast it. Otherwise, it will be throwing long, and the system may not pick correct answer all the time. It may pick correct answer, it may not pick. You can do typecasting yourself, or otherwise you can just see if it is working, it's fine. Generally, for the companies where the backend answers are not shown to you, and also they do not show whether you have passed all the cases, like Microsoft, there you wouldn't want to just return the value, because you should not believe in what compiler they are using, what things they are using. It may work on all the compilers that you have seen, and it may not work for someone else, internal compilers. So even if it is on hacker rank, then at least you can understand, because you can see you have failed something, and you can do something for that, right? So this is a structured code, but we have also seen all of these things already, right? So there is nothing new in that. So I'm expecting that you can do this and you can consider it done, but I have one more problem in the assignment, but I have made a video for that. So I think it should not be a big problem right now. Okay. So matrix exponentiation is done. And thankfully, from the next class, we have one class per week. So even though the topics are going to be little bit, difficult type, difficult means you will be seeing new things. So that is difficult, right? Otherwise, if you know it, then it is easy. Not knowing is difficult. So, but we have only one class. So that's pretty much doable. So we will have Saturday class in the morning. Okay.